Professor Kawasaki, hello.
Hi. Good morning.
It's difficult to combine your time zone with our time. I think it's about midnight.
It is 10 p.m. here. That's okay. That's okay. I feel sleepy. I think it's, but that's fine. I'm appreciate there are 15 people here.
We're still waiting. Yes.
Yeah, that's great. I was expecting like maybe 5 people in the morning. Nobody come, and then that's great. 15.
This is disadvantage of online conferences, because if you are in Magnitogorsk, you are in Magnitogorsk, and
Oh yeah, right. So right, for them it's not. It's 10 a.m. It's
yes.
going to be 10.
Yes.
So that's okay for them.
Okay.
Right. That's good. Okay. Oh, there are several people. Okay. I cannot see.
Ну, наверное, старший научный сотрудник института. В этом... Дима, меня слышно?
Да, слышно. Dear colleagues, thank you for your, first of all, thank you for your attention and participation in general. We are starting the second day of our Magnitogorsk Materials Week in memory of Professor ZHILYAEV. And this day we will open by report of Professor Megumi Kawasaki from the USA. It was difficult to combine all time zones, but anyway, thank you for your attention. You are welcome.
Okay, am I going to start?
You can start your
Wait, or maybe not yet. Is it 10 o'clock? Or I can put my slide there. Is it right? Oh my, what am I doing? Where's my slide? Where is my slide? Let me see. Okay, so I am sharing my slide. Okay. Is it okay to start? Or am I going to start?
Yes, yes.
Okay, great. Thank you for coming. I just surprised. There are 21 people attending, including me. So there are 20 people additionally. Thank you so much. I thought it's early morning for you. So late night to me. So it is great pleasure to have us.
You're a hero.
Thank you. I was thinking to have a wine, but I was already sleepy. So I thought it's better not to have. So I hope I'm not going to sleep during my talk. So today, my talk is very similar to what I heard in a four meeting, Magnitogorsk materials seminar in fall 2020. So if you heard this, if you had my talk before, and I am very sorry, it's quite similar, but I put a little bit of new thing. But especially this meeting is dedicated to Alex ZHILYAEV. He's very good friend of ours. So it is sad, but his work is excellent. So we are going to follow how he did in the science. So I know yesterday there have been really nice talk, and I know Professor Langdon showed pictures of Alex, and I am following the same way as he did. So from when I was student, so I had the picture with Alex ZHILYAEV when I start to have academic job, but even before that, when I was a graduate student, I met him many places in the conferences, and then usually like once a year, twice a year in the conferences in the different places, we met, and then we just took a photo in the many different places. So these are the photos I could find in my computer. So from 2012, and then several different TMS conferences in the US, and then 2018 in the Superplasticity Conference in St. Petersburg, and then 2019, so in the US as well as I visited Magnitogorsk. So we met him several places, and then it's really nice memory. Then in 2019, March, right, I visited Magnitogorsk, and then there was a 1 week meeting. So this was a nice picture with Alex. And then later on, me and then Roberto must be somewhere, I could see his name. Roberto, we are friends, we are really good friend. We did the study, graduate study in the US, in Los Angeles together. And then, of course, with Alex, we made a special issue in Advanced Engineering Material, and then that was published in January 2020, I believe, 2020, sorry. So it was actually my maybe almost last walk with Alex while he was alive. So it was really nice. And then just one, wait, I think I have a slide. So I was checking his progress. Even today, it's keep changing every day. There are so many excellent papers of him, and we are citing his work. So I see the change in the citation number and H index of him day by day. So here is a list of the Alex progress so far. Today I checked, so that's April 5th here today. So he has so many citations, it's excellent. And I was watching the record of those from top, and of course, we know everything, but especially the top, the fourth, that is a book. Actually, I don't know you are watching my picture or not, but this is a book I have, and I remember the book was published with Professor Langdon and Professor ZHILYAEV, and then this book was published in 2014, and I remember there was some small ceremony in a TMS conference. And then I bought the book in the conference. And then it was a good chance to ask Professor ZHILYAEV and Professor Langdon, as well as Alex, give me the signature or some message. So here it is. Here there is a message. I hope you can see something. But the interesting thing was that Professor ZHILYAEV wrote some message. Professor Langdon wrote long message. And then it is Alex is Alex, always. He's like that. He said, he told me, I know him. Well, because he knows me, I know him. So he doesn't need to put any messages. So he just gave me the one signature of him. He just put his name and his signature, that's all, without any message. So that was a great part of Alex. So I have his signature at least in my book. Then that was a great memory with Alex. So those were about the personal things. But here, Alex and I, with my collaborators together, we have done a lot of work from especially to 2015 and later on. So maybe some of you know, and I could see in the program yesterday afternoon, there was several talk about the high pressure torsion and the mixing of dissimilar metals using the high pressure torsion. So that was also done with Alex. Actually, Alex gave me that idea. Why don't we do the high pressure torsion, but put several different metals together? And then we will see how it goes. So even though in this slide, it looks like I studied a lot, like for the background of this study, but basically the idea came from what Alex suggested to me. So let's do like a sandwich of the metals using the high pressure torsion. So using the high pressure torsion machine, previously I was in South Korea. Now I moved to Oregon, US. So we do high pressure torsion but put the several different metals, and we are going to see how the microstructure change and also property change. So in the beginning, what we published with Alex was with using the aluminum and the magnesium. So put the aluminum metal and the magnesium in the middle. So usually why we put, or how do we select the material in the middle and then something outside? So I actually studied several, like as a background study, I read several papers in related to the accumulative low bonding. They are also doing something similar thing. They put the layers of the metals and they do the accumulative low bonding. But there are several papers talking about the difference in the hardness of those metals. So if we want to see the better mixture of two different metals, just not only making the layers of the metals, but if we want to mix the dissimilar metals really well under the severe plastic deformation, it's better to put the hard material in the middle. And then especially if the hardness is very different between those two different dissimilar metals, then the better way is to make the hard material even thinner than the soft material that should be thicker, then put under the severe plastic deformation so that they start to mix really well. So based on that knowledge from the accumulative low bonding, we start to process these similar metals using the high pressure torsion. And we published those some of the study in those papers and then several more. So using aluminum and magnesium. So in this case, I put the aluminum outside, magnesium in the middle, and then we start to do the high pressure torsion with a different, under the 6 gigapascal, but increasing the number of turns. So now you see the cross section of the sample after the HPT sandwich process, 1 to the 10 turns, and then also hardness plot, hardness like color code map in the bottom. And also you can see the plot of hardness versus distance from the disk center. So what you can see here is after 1 turns, those metals stuck really well. And then there was no segregation, there was no void, visible void. But after 5 and 10 turns, you see the disk edge, especially where there is a higher straining happening. The magnesium phases start to be smaller, and then at the end, after 10 times, you see the magnesium phase dissolve in aluminum matrix. When we measure the hardness in the bottom, you can see that the edge, disk edge, where the magnesium start to be separated and then dissolve, hardness became really high. That high hardness is the hardness we cannot even achieve with just processing of aluminum and magnesium. Sorry, my brain's sleeping. Aluminum and magnesium, if we just process separately, there is no way we can get that high hardness. So there is the very unique and then significant micro grain refinement, as well as like phase transformation is happening at the disk edge. So we start to measure the microstructure after the 10 times where the hardness was really high. So the grain size was reduced really small in just 10 minutes, room temperature under 6 gigapascal. So then the grain size was really small, reasonably equiaxed, and 90 nanometer was the average. But also in the disk edge, from mid radius to the disk edge, we found the two different type of the intermetallic compound. One was aluminum 3, magnesium 2. The other one was aluminum 12, magnesium 17 in a very small volume, but small grain size with the two different intermetallic compound was observed. So actually we could create the area, especially at the disk edge, forming the intermetallic based or aluminum metal matrix nanocomposite. So then next one, so those intermetallics came out with the thin layers. Actually, it's a borderline of the or interface of aluminum and magnesium phases. But those, there was no way so far. We couldn't really control the volume and also the location. So when we see the intermetallics, we know where they are when we do those chemical analysis, but we cannot really control the volume or amount or the location to place those intermetallics. So you can see the layers of aluminum magnesium interfaces, and they are just like heterogeneously distributed. And then we increase, I'm just watching the clock just in case. So we increase the number of times to the 20 times. And then also we know if we increase the number of times, material just get brittle. So to also give the ductility, we know there will be some recovery, but it's also good to consider the ductility. So we apply the 20 times, we increase the number of times to 20, and also we apply the post-deformation annealing for 1 hour. And then here again, you can see the cross-section of the disk after high pressure torsion of aluminum outside, magnesium in the middle. So the disk center, you see it's the same structure like aluminum, magnesium, aluminum. There is a clear border. And after 20 turns and also 20 turns plus annealing. But at the disk edge, it's quite similar microstructure. We could see after 10 turns. So magnesium chunk was become really small and then just distributed really well. So we don't, in this color after etching, we don't really know it's like there is a magnesium chunk, like phase still there or dissolved completely. And then we measure the hardness so that the hardness after 20 turns at the disk edge, it goes to really high. That's so far highest. And then after annealing, of course, there is a recovery. There must be some grain size, grain growth as well. So the hardness go down, but still it's reasonably high. So then when we see the microstructure at the disk edge, after 20 turns by HPT and after HPT plus annealing, you can see, let's see, after high pressure torsion, 20 turns at the disk edge, grain size was reduced further. So now you see the grain size at average of 60 nanometers. And then we could see the layers of intermetallics in bigger volume than the previous sample. So after 10 turns, that was quite small, but after 20 turns, now you see the intermetallics volume or volume fraction increased more. So that made material hardness higher. Then after additional annealing for 1 hour, short period of time. Now, what we can see is a very equiaxed grains with the average of 380 nanometers. And then still we could see intermetallics, aluminum 3, magnesium 2. I think there is aluminum 12, magnesium 17 as well. But the interesting part after the annealing was not only, we don't see the magnesium phase, but we saw aluminum rich grains, aluminum rich phases, grains, but also some of the grains start to have aluminum and then magnesium solution grains, solution phases. So one of the examples here you can see is aluminum 7% magnesium grains or phase. So magnesium actually start to dissolve in many places, either making the intermetallics or making the solution condition. Then next one. So after high pressure torsion 20 turns and additional annealing, because annealing was done for improving the ductility. So we did nano indentation to see how the strain rate sensitivity go up or how it changed. So here you see the typical load displacement plot for the left one. Okay, so after HPT for 20 turns, and the second one is a HPT 20 turns plus annealing. So you see the difference in the load displacement curve. So displacement is very small for the material which is brittle. So you see the just only high pressure torsion material become really hard and brittle, so that the displacement is small for 4 different nano indentation strain rate. But after annealing, materials becomes reasonably soft, not really soft, but became like a little bit ductile, so that the displacement become larger. So then we can measure the strain rate sensitivity from the plot of hardness, or actually converted yield strength versus strain rate. Then we see the big change in strain rate sensitivity value, M value. So we can see that additional annealing after deformation, so post-deformation annealing made the material ductile. So the interesting part of applying the high pressure torsion on the dissimilar metals, 2 different materials, is not only making the material strong, but also we can make the mixture of material really well. So after 5 to 20 high pressure torsion on the aluminum magnesium sandwich, what we could see was we actually changed the physical property. So basically density. Here you see the density of aluminum and magnesium, ZK60. They have typical aluminum magnesium densities, even though after HPT, of course, density doesn't change. But after high pressure torsion on the 2 different metals, aluminum outside, magnesium in the center, and we mix for 5 to 20 high pressure torsion, then you see the density is just keep going smaller. So initially after 5 turns, it was still close to the density what the aluminum had, but with increasing number of turns and more, the great mixture make actually the density of the material lower. So we measure the density, especially at the disc edge. So here you see in the left side drawing, or actually picture, we remove the central part where we know there is a magnesium chunk, magnesium, like large phases exist. So we remove the disc center and we measure the density at the disc edge. So then density goes down, but we know the hardness goes up. So actually we can make the very unique material which has high strength, high hardness, but actually the material has very high specific strength to the weight ratio. So with this very quick room temperature processing on the 2 different metals, or you can mix 3 different metals and process at once, short period of time, and you can make very unique material. And then we increase the number of turns to 100 turns. So we just wanted to see actually how the central part of the disc change when we apply high number of turns. because we increase the number of turns up to 20, and then later on we increase to 40 and 60 turns in a different publication. But we did not see the homogeneous hardness. We could not achieve the homogeneous hardness. So we just thought, why don't we just increase the number of turns to 100 and let's see what's happening. So then after 100 turns, and then this is the cross section, we know the material become really brittle, so that while we are cutting the sample, some of the part, like here, it was taken, but this was not during the processing. This section was taken during the cutting. So we know material became really really brittle. But when we just cut, and then it was really interesting that in the disc center, we did not see any trace of the magnesium phase. And then all over, it was just really similar. And then when we measure the hardness, on the left side, you see the plot of hardness versus distance from the disc center. The 100 turns was shown with a green dot. So you see the hardness now get the homogeneous hardness, about the homogeneous. So as this microstructure in an optical microscope, it says hardness or material actually became really homogeneous. And then we did the TEM at the disc center and the disc edge. And then this is a beautiful TEM photos that the equiax grains at the disc center, disc edge, they are really identical, showing the average grain size of 30 to 40 nanometers. So now we could make the material really homogeneous. And then we know the magnesium dissolved completely in aluminum, but we thought there must be flow of intermetallics. Maybe we could make the bulk intermetallics. Then we did XRD, and then that was an amazing result actually. So now you see in the XRD plot, the bottom two are the just references, but top two line, blue line and green line, those are the result after the 100 turns. And we left this disc for 2 months in a room temperature. So actually my student was putting the sample in his desk for 2 months. So that was exactly 2 months. Then we measured the structure. So how it goes. And actually it was really interesting that we did not see any intermetallics. That was just bulk FCC structure, basically aluminum solid solution. So you see the aluminum magnesium 100 ton, that was measured right after the HPT. And after 2 months natural aging, it was almost the same XRD profile. But obviously you see there is a peak shifting with the peak broadening as well. So we know the grain size becomes small. There must be the peak broadening, but there is a huge peak shifting after the 100 turns with the magnesium dissolve inside. So from that shifting, we could just calculate simply that the average 14 to 15 atomic percent of the magnesium dissolve in aluminum and making or showing the FCC structure. So it was amazing. Actually, it's a supersaturated solid solution. So this bulk material, we could actually make the metastable supersaturated solid solution material. And then further analysis, like the compositional analysis was done with using the STM. So we measured a lot of points and then see how the aluminum and the magnesium amount are. And from the disc center to from disc edge, those values here you see in the table, those are just references, but we measure quite many points. And then we found actually the magnesium amount was very different everywhere, not only the center or edge, everywhere in the mid radius in the same way. Some of the locations, they were close to like pure aluminum, like 0.1, small amount of magnesium. But some place in the disc center, disc edge, we could find a huge amount of magnesium, even more than the average value of 15 atomic percent. The highest one was actually around 40%. So we could see the supersaturation of magnesium everywhere, but the magnesium was distributed heterogeneously. So that heterogeneous distribution of the magnesium made actually in the X-ray XRD peak, not only the sharp peak, but actually you see the shape of the plateau XRD profile. So that came from the many peaks of FCC aluminum having the different amount of magnesium, showing the compositional broadening. So here you see the schematic drawing of those plateau-shaped XRD peak made of many peaks with of aluminum having a different amount of magnesium. So this material, after 100 turns on the aluminum magnesium sandwich, we could find the homogeneous grain size and homogeneous, basically, aluminum solution. But there is a huge heterogeneity in the distribution of magnesium atoms. So that was published in 2019. And then, okay, so still there is a additional analysis we have done in 2020. So that heterogeneous distribution of the magnesium, we know that heterogeneity will definitely make the huge microstrain in the crystal. So we measure the microstrain, and then we could see in that small grain size, 30, 40 nanometers, and the microstrain the material had, this metastable material having the supersaturated solution state, they have huge microstrain in the lattices. And also we could expect not only the grain size reduction, that supersaturated solid solution definitely contribute to the high hardness of the material. And then, so we could roughly estimate, briefly estimate the effect of solid solution strengthening, bringing that huge or extreme hardness this metastable material could show. So that was about the 100 turns. And then we could do that sandwich high pressure torsion process with using the different materials. So we have done with aluminum copper. So these are the cross section of the discs after 10, 20, 40, 60 turns. So you see the mixture, good mixture of aluminum and copper from the disc edge. And then where there is a really good mixture, you see in the bottom plot, hardness versus distance from the disc center. So the disc edge hardness will go up, and that high hardness will be higher with increasing number of turns. Then next one. I know I'm watching the clock, so I don't want to be over, but I think I may talk a little bit more, like 7 more minutes. So here is additional analysis on the aluminum copper sandwich process. So after 20 turns, the microstructure became really fine, but they made a layered or ultrafine layered structure with the thickness of the layers 20 nanometers. And after 60 turns, you see the grain size become quite equiaxed with the average grain size of 30 nanometers. We did XRD so that we could find the good amount of aluminum to copper intermetallics. I think we found several different intermetallics of aluminum and copper. But this aluminum to copper was one of the large number of large volume fraction we could find in this aluminum copper processing. And also additionally, we did the wear testing. So just tribology testing on the surface of the material. So here you see the 3D depth sensing photos for the 20 turns and the 60 turns disc surface. So what we did is we scratched the disc surface with a different applied load. So especially we focus a higher load. So here example, it's shown at the 30 Newton. So when we scratch the surface with 30 Newton for totally, I think I don't remember exactly, but I think 1 meter, just scratch with certain strain rate. And then we could measure the wear rate, that's how fast the volume of the material was taken from the surface. So higher wear rate means material was taken a lot, quickly. So it's actually not good. So with the 30 Newton of application on the surface and a 20 turns disc, you can see a lot of volume was taken from the disc surface. But after 60 turns, you see 30 Newton was still not very high enough to remove a lot of volume on the surface. So material got high wear resistance. So increasing hardness by increasing number of turns, wear resistance went up on the sandwich aluminum copper material. And in terms of the wear testing, I think I have next slide. It doesn't go. What's happening? Okay, so in terms of the wear test, we also did the wear test on the aluminum iron, aluminum sandwich. So aluminum, we did only 20 turns under 1 gigapascal because I think we did the 6 gigapascal and the material started to slip, didn't mix really well. So we applied lower stress and then lower force, and then we applied the 20 turns. So then they actually did not show the intermetallics, but you see in the bottom STM picture that the aluminum and the magnesium start to mix quite well at the disc edge. And then the microstructure get defined after 20 turns, ultrafine layer structure with the thickness of the layers of 20, 30 nanometers. And after the wear test, we did not have any other discs. So we just did the wear test on this surface of the 20 turns material. And then what we could see was wear rate was not that high after scratching on the surface. And then we could see on the cross section of the wear surface that actually aluminum phase was blocking from the wear. So that the aluminum is basically soft, even though there was a grain refinement. So aluminum was taken, but once wear surface reached to the iron phases, iron was actually blocking from the wear. So wear resistance was increased, or wear was protected by the iron phases. That was what we could find. And then next slide. Okay, let me see. Okay, so here is a mechanism that was explained by the other researchers, that in the macro scale, what we are making with aluminum, not aluminum only, but the different metals, and then we process, we apply the shear. What we made is actually called by the called as a tribal materials. We apply the shear, so we like scratch each other, and then there is a new phase, new material is formed at the interface of dissimilar metals that specifically we call as a tribal materials. And then the formation of the tribal material, especially under the high pressure torsion, was due to the plastic instability. So because we applied the two different materials and they have different strengths, so then we apply high pressure and torsion. So that difference in the yield strengths of the dissimilar metals, they start to have termination of the severe shear at the interface that make a plastic instability, and they start to have a turbulence of the plastic deformation. So that was explained well with those drawings. So actually with the high pressure torsion sandwich processing, we are making a huge amount of the tribal materials, especially after 100 turns. All material actually became the tribal materials using this this sandwich process, but actually it was due to the plastic instability of dissimilar metals. So then next one, I hope. Okay, so we can explain that the mixture of the good mixture of the different materials. So in this case, aluminum, magnesium, and aluminum copper from the disc edge with increasing number of turns. And I wanted to explain, is that there is any relationship with the equivalent strain we can calculate with depend on the location of the disc, right? So that the good mixture area and equivalent strain we apply, actually there is a relationship, and we can calculate or we can estimate when we are able to get the full body of the tribal materials with increasing number of turns or with the increasing equivalent strain. And then next one. Okay, it's going back. Next one. So we can also apply different number of discs, not only just 3. We can just increase the discs. The good part of increasing the number of discs is we can accumulate, or we can accelerate the mixture of the dissimilar metals. So that was done. That was done in the top using aluminum and magnesium. Just put the 5 different discs, and then we could accelerate the mixture. And also that was done with several researchers with several papers, but I'm always using the same example, kappa tantalum, putting the many different layers. It's totally 37 layers of the thin film, and then do the high pressure torsion so that good mixture of those can be, those metals can be found quickly. And then next, we can also increase the size of the disc if we can design the different die. So example was shown with a 1 inch, that a 25 millimeter disc with a thickness of like 3 millimeter or a little bit more. But because the disc become bigger and the high pressure torsion force capacity is limited, so we could apply the lower force, lower pressure. So unfortunately, aluminum magnesium, when we process, we could not really show or produce the intermetallics currently. And then next one, aluminum, titanium, aluminum, we could do that. I have limited time, right? 3 minutes, okay. So I could finish, okay. There are example, I'm also showing the same slide, but just one. Recently, other group, not my group, but other group was also showing the good or interesting material combination of niobium, zirconium, niobium. That was often used in accumulative low bonding process, making the nano layers of niobium and then zirconium. But here, when you apply the high pressure torsion, we are not able to make the nano layers, but actually making the complete mixture of niobium and zirconium. So that must be the good paper to read. Okay, then I think I should, okay, I should stop this talk today. So here, I got a lot of idea from Alex ZHILYAEV, and then here we just need to continue that our good study as we learned from him. So then thank you so much for listening. 35 people, thank you so much. Okay, so I am going to stop sharing. Thank you so much for listening.
Thank you, Professor Kawasaki, for such a brilliant report. You can make a great presentation at any daytime.
I was sleeping. My brain was sleeping. Thank you so much.
But it was great, and thank you for touching story about Professor ZHILYAEV. So, colleagues, do you have any questions? Don't hesitate.
Hi, can I ask a question?
Yes, of course. Yes, please.
Yeah, thank you for your great report. I have a couple of questions. As I see, your main method of investigation of mechanical properties is to measure microhardness. Did you try tensile test with such samples?
We have tried, but so far, when we make the micro tensile sample, that the gauge length is locating in the radius of around 3 meters from the disk center. So it was not really the location we wanted to measure the ductility. So we tried, but the result was not really what we wanted to get. Or often when we prepare the sample, it was not really homogeneous, or let's say, it was not good accuracy, maybe because of the heterogeneity of the material. So we didn't really have a good series of the result. And we did not do the tensile testing for the metastable material, even though we got the homogeneous microstructure. I know it was just hard and brittle, so we didn't really try. So it was definitely good to try, but so far we didn't get a good series of the result. That's what I can say.
And the second one, did you measure thermal stability of structure and mechanical properties of such?
Right, that's a great question. Actually, so only that 20 turns plus annealing, that was done. We really applied the heat. And the metastable material, actually, we are doing a heat measurement, actually, with my collaborator, Klaus Dieter Lies. He is here, actually. So I think he may give some good like example. Maybe not this material, but we are doing that, yes. Heating and see how the thermal stability goes.
Okay, and did you try it through time, I don't know, to see the same sample after a month or 2 months, not without any heating?
So that was the only thing we have measured, so that's why we published. But after that heating one, it's still like ongoing like research. We did not have a series of the result, so not yet.
Okay.
Please wait a little bit more.
Okay. Thank you.
Maybe in the next meeting, I will be able to present some of the result.
I will be there.
Thank you.
And
Oh,
one question from Professor Korchinov.
Dear Megumi, first of all, thank you for a very interesting.
Hi, thank you for listening.
For a very interesting night presentation.
Thank you. Every time it's night, right? When I talk to you.
My question is about the friction condition during the HTP process. How do you evaluate the value of friction coefficient during this process?
Friction coefficient of the, so between the aluminum and the magnesium or aluminum copper, for example?
Yes.
Those we did not really measure. We wanted to, but so far, no. It's difficult. But when they slip, there is a sound. For example, when I process aluminum and iron, there was a huge sound and then they didn't mix. So that's why we don't know the value of the friction between the metals, but we just stopped. Because I know that sound, they are not really mixing. So we had to change this processing conditions.
What is your opinion? How does it influence on the changing of microstructure after process?
After process, so far we tried increasing number of turns to, let's say, 100 or 150 turns, and we can, if they are good in a good mixture, they are going to make solid solution. But if it's a immiscible metals, and they will make maybe bulk amorphous structure. Maybe I didn't try yet. That can be done in the researcher here now listening in here.
Thank you.
Okay, thank you so much for listening. Thank you.
Thank you. We should go to next report from Professor Zhu from University of Hong Kong, China. Professor Zhu, you're welcome.
Yes, thank you. Let me start my.
We see your presentation.
You see it? Okay, great.
Yes.
Is it okay now? Can you see me?
Yes,
I mean the presentation. Okay, great. Okay, first, I'd like to thank the organizer for giving me this opportunity to present at this conference honoring Alex. I've been friends with Alex for many years in the area of ultrafine grained materials, and we often see each other at TMS meeting and other international conferences. Today, this talk, and I present this talk to honor him. So the topic of my talk is heterostructured materials. New science enables superior properties. I moved to the City University of Hong Kong last July. So I've been here for less than 1 year. First, I'd like to acknowledge my collaborators, Professor ZHILYAEV, Chongxian Huang, and Xiaoxi Huang, Hua Jiangao, and others. Okay. We know that we have a big problem right now in the world, which is pollution, global warming, and also energy crisis. Okay, then we will ask, what can we do as a material scientist to contribute to the solution of this problem? We are working on structural materials like metals and alloys. If we can make them strong and tough, those materials will can be used to make energy efficient transportation vehicles that can help with solving this problem. This is especially important for the electrical cars, for them to have long distance per charge when they charge the electricity. For metals and alloys, we all know that there is a banana curve. Like shown here, the strength and ductility. So a metal can be either strong or ductile, but it's very hard to have both. And so, for example, the nanostructured metal, they are very strong, but ductility is so low that we do not want to use them. It's not safe. Of course, coarse-grained metals are often ductile but weak, not so strong. So for real applications, we would like to have both strength, both high strength and high ductility, but unfortunately, that's not available in most cases. Then you may ask, how do we make a metal strong? So this is relatively easy. If you look at our textbook, you can do solution hardening, precipitation hardening, like for aluminum alloy, this second phase hardening is very important. And grain refinement, that's what we have been working on, ultrafine grain on nanostructured metals. So that's on the principle of smaller grain size. Code working, we all know that when you do the code working, the dislocation density will increase, they become stronger. However, high strength alone is not good enough. We also need high ductility or good ductility for real applications. Otherwise, it won't be safe. So how do we make a metal ductile? That turned out to be not so easy, not so straightforward. Before going further, I'd like to state that ductility is always measured under tension, under tensile test. Let's look at how a sample fails under tension. Before it fails, it often starts necking first. Of course, for brittle materials, if their plasticity is low, they may fracture. But for most metal with high plasticity, necking occurs first before failure. So to improve the ductility, we have to delay the necking or prevent the necking. So to do that, we can use, there are two criteria to judge the necking, the start of necking. Firstly, the hard criterion. In hard criterion, this is the d sigma d epsilon. That's the slope of the stress strain curve. Sigma is the flow stress. M is the strain rate sensitivity. Okay. Yeah, room temperature, but this M is often very small. If we ignore M, because of that, you have considerably criterion here. What it simply saying is the slope of the stress strain curve or the strain hardening rate is higher than the flow stress. This is the problem. Like if we look at this nanostructured metals we all have been working on here. This is one example for nanostructured titanium. See, this is coarse-grained titanium. This is nano titanium. You can see nano titanium is much stronger than coarse-grained titanium. However, look at its strain hardening rate. This is under compression, okay? Under compression, there's no necking. You can press it to larger strain. Look at this. The slope is close to 0. You got a high flow stress, and with this go to 0, sigma is very high. You can imagine the ductility will be low. So not surprisingly, on a tensile test, once you get to the high stress, it quickly, the stress drops and necking starts around here, okay, before the highest point here. So which is why the nanostructured titanium, nanostructured metals will often have low ductility because you need higher ductility for high stress, for high strengths, but your ductility, your strain hardening rate is even lower with higher strengths. So ductility becomes lower. That's how we get that banana curve. You know, we have been studying metals and alloys for over a century. Now the question is, do we have anything we do not know? Any new unexplored mechanisms to improve strength and ductility? Is it possible to have any new breakthroughs? With that question, I'd like to introduce a new paradigm on materials design and its theoretical basis. This is what I call heterostructured materials. Basically, it's non-uniform materials. You know, in the industry and in the past, we often stress that we want a uniform structure. But now we are saying, no, we want non-uniform structure. This heterostructure can simultaneously increase the strength and the ductility and the work hardening rate by this so-called heterodeformation induced hardening or HDR hardening. I will tell you later what is that. Conventional strengthening mechanisms often decreases strain hardening rate, leading to the well-known banana curve. But heterostructured materials is an exception. So now you may ask, what are heterostructured materials? What's the definition? The definition here, we have the two criteria here. First, they need to have a large strength difference among different zones. It's larger than 100%. Why 100%? Because we need to draw a line somewhere. Secondly, it needs to have significant synergistic effect. I call that 1 + 1 larger than 2. Using these criteria, the following structures can be called heterostructures. The first is the gradient structure, like this one. There's a nanostructure on the surface, coarse grain in the center. Laminated structure, like this one. And harmonic core shell structure, this one. And heterogeneous lamina structure, that one. This is also bimodal structure, multi-phase structure, which is not shown here. But if you look at this cartoon, these structures look so different. You may ask, how can you put them as under one category? We call them all of them as heterostructure because they have a superior property due to the same fundamental theory basis, which is the strengthening and work hardening induced by HDI stress. By the way, this definition is presented in this recent paper in MRL. You can see there are like 14 authors from all over the world, from US, Korea, Japan, Europe. And so with this, we're announcing to the world this new field called heterostructured materials. And what's idea hardening? If we look at, using this cartoon, if we assume this X is a Frank source, at immediate dislocations, they all slip along this slave plane and got stopped by this zone boundary. So nanostructured domain or zone is a consequent zone. When they pile up here, it prevents multi-silicon to follow them because they collectively present a long-range back stress to block following dislocations. This long-range stress is called back stress. Okay, and with this, you can also see there's a dislocation distribution gradient here. By the way, these dislocations, they all have the same Box vector because they are from the same Frank source. So they are called geometrically necessary dislocations, or GNDs, because they produce a lattice distortion collectively. And so in this grain, there will be a string distribution will be like this, because at the boundary, there's no dislocation reached it, which means the plastic strain is 0. Away from it, you got higher and higher plastic strain. So you have a strain gradient. This strain gradient is accommodated by GNDs. Basically, with this cartoon, you link all this up. Dislocation pile up, which means the GNDs pile up. And you have a strain gradient, you have a back stress plus forward stress, and that produces ideal stress. I will explain forward stress in the next cartoon. Okay, let's draw, so in this cartoon, we see this is the dislocation piling up. We all know from our textbook, at the tip of this piling up, there's a stress concentration, which is N tau A. Tau A is the applied stress, and is the number of dislocations in the pile up. So this stress concentration needed to be balanced in the hard zone by a stress which is also N tau A with same magnitude, but in opposite direction. So that is the forward stress. At the boundary, the back stress and the forward stress, they are same in magnitude, but opposite in direction. At the boundary, they balance each other, cancel each other, but away from the boundary, they decay in a different way. So collectively, they are not totally canceled. And collectively, they produce the so-called ideal stress, which can be measured using mechanical testing, which I will show you later. So dislocation piling up can take different forms. The first form is this piling up along one slave plane. This produces a strong ideal hardening. This is piling up against the boundary. If they pile up like this, one on top of each other, we all know what this is. This is the small angle grain boundary. This piling up does not produce any long-range back stress or forward stress. So there's no ideal hardening here. If it's a mixed type, the piling up it produces a medium effect. For statistical stall dislocation like this, all the box dislocations are random with random box vector. So they do not have a long-range stress, they cancel each other. So these are statistically stalled dislocation. They produce no back stress. Traditionally, when we talk about how dislocations affect the strength of flow stress, we use this HB equation. This is the square root of dislocation density. This is total dislocation density. Rho S means statistical dislocation density. This is G&D density. So basically, it only takes into account the total dislocation density. The HDS stress produced by G&Ds are not taken into account. They are simply ignored. Then you may ask, for the past 100 years or 50 years or several decades, why have we have been using this equation, SBD equation? It has been okay. It is okay because in conventional materials, this HDS stress is very small. Without it, we can explain our mechanical behavior quite a while because they are so small. Although, conventional uniform structured materials, they also have grain size variation and grain boundary, all those. They do produce some HDS stress, but very small. However, in heterostructure, that HDS stress is very high. You cannot ignore them anymore. So we use the HDS strengthening can improve the strength. And then it can also retain that improve the yield strength, HDS strengthening. The HDS hardening can retain or even increase ductility. As a result, it produces a combination of high strength and good ductility that is not accessible to homogeneous materials. Okay, here's another cartoon that explains this principle. If we use dislocating hardening, assuming that's look like this rock raised above the water, like with higher dislocation density, you get higher flow stress. If that's a rock, it is HDS strengthening or hardening is the beacon, which is much higher than the rock, is above the rock, built on top of that. So as a result, it gets very good property. Okay, as I said earlier, we want to both high strength and high ductility. We can never get it. And next, I will present you one example that is doable. This is laminar structured titanium, because this is one type of heterostructure laminar structure. The coarse grained titanium with a grain size about 44 micrometers. With the cold deformation will produce ultra fine grained structure. And then we did a partial recrystallization. And with 25% by volume recrystallized. And you see this is recrystallized reading. It apparently has a large grain and clean without dislocations inside. And this is the matrix, which is non-recrystallized ultra-fine grained titanium or nanostructured titanium. So this is the hydrostructure. Now you look at the strength and the ductility. Here's the uniform elongation, which represents the ductility. For coarse grained titanium, it has a low strength, relatively high ductility. For ultra-fine grained titanium, it has a strength increased from 300 to 900 megapascal. Ductility decreased to about 2%. It's not surprising. It follows the typical banana curve. But for heterostructured titanium, you see it here. The strength is close to ultra-fine grained titanium, but ductility is even higher than coarse grained titanium. Okay, now here's some problem with this data. First, we have 25% by volume with a larger grain size, which is about 4 micrometer on average. According to Hall-Patchy relationship, the strength should come down. Now the strength did not decrease. That's violating the Hall-Patchy relationship. Secondly, when we did a partial recrystallization, the dislocation density got dramatically decreased. According to the HB equation, the strength should also come down. The strength did not come down. That's violating the HB equation. Thirdly, if you look at the strain hardening rate, Here's the coarse-grained titanium. This is ultra-fine-grained titanium, which is lower than coarse-grained titanium. For heterostructured titanium, however, their strain hardening rate is higher even than coarse-grained titanium. So that's really violating the rule of mixtures. So this result are violating everything we know from a textbook and the literature. That's due to the HDI strengthening and HDI hardening. Here's from microstructure wise, how do we explain this? If you look at this grain embodied in ultra-fine grain matrix, you look at this, all these green lines along it, all the dislocation piling up. There are so many dislocation piling up, I'm counting them here. So what's happening, assume this strength, this larger grain has a relatively low strength of 500 megapascal. When this dislocation sort got started, the dislocation got all piled up against the boundary. It cannot go across the boundary to go to the matrix because the matrix is much harder, much stronger. So as a result, it makes this larger grain stronger and stronger until the matrix started to yield. That makes this grain almost as strong as the matrix. So that's why the strength doesn't come down. Okay. And this cartoon is, this is the after tensile test. You see all these larger grains, these colored grains, they are elongated. But this before the tensile testing, they are equiaxial because they are all recrystallized grains. And by the elongation, when we calculate their strain on average is about 45%. The sample total strain is only 9.4%, which means these larger grains are taking a lot of strain. There's a big strain difference between them and the matrix. So, however, at the boundary with the matrix, the strain got to be same. There's a strain continuation. So that also means near the boundary, there has to be strain gradient. As we said earlier, with the strain gradient, you have GNDs, you have back stress, forward stress, and you have HDI hardening. Okay, that's some proof here. Then you may ask, how much is the HDI stress? Can you measure it? Yes, we can measure it. This is in titanium. This green curve represents the HDI stress during the tensile test. The red curve is the conventional dislocating hardening. You can see this green curve is much higher than the red curve in this heterostructured titanium. For conventional titanium, uniform structured, this green curve should be much lower than the red curve. And in that way, they do not play a much role there. But here, it's so high that we cannot ignore it anymore. How do you measure it? Here's a paper here. You can measure this. You can, I don't have time to go to details. If you have more questions or need more papers, send me an email. I can send you more papers. Here's my email address. So compare dislocation hardening to the HDI hardening. The dislocation hardening is isotropic, non-directional. The short-range dislocating interactions caused by short-range dislocating interactions is related to total dislocating density. HDI hardening is not well understood. It is a long-range stress, is a kinematic, the directional, always opposed to the applied stress. It is related to piling up of GNDs, is correlated with the Bossinger effect, which means heterostructured materials always have very high Bossinger effect. Then you may ask, how do we design heterostructures to have superior properties? Here are a few principles. First, you want to have high density of interfaces because that's where this dislocation piling up occurs. Secondly, you want to have appropriate interface spacing because you want to leave enough space for dislocation to pile up. Thirdly, you want to have full constraint of the software zone, because it's like a soft zone embedded in hard zone. This is the opposite to our conventional concept. When we want to strengthen some material, we always have the hard zone as the minority. Here, the soft zone in the minority. So this, if a soft zone is not fully constrained, they could flow around the hard zone, and your strength will not increase that much. Okay, this is spacing, interface spacing, and our current result shows is like a few micrometer size, give us the best result. Here's one example. On this, when we try to study how what will be the interface density, and we have the theory about this distribution density in the string gradient and all those. We want to see how the interface affects the mechanical property. First, we did the copper brass layered structure. So with the thickness decreases, this strength increased, the ductility also increased, which verifies that the higher density of the zone interfaces, you get better properties. However, it's not the smaller the better, and there is an optimum size below which it will further increase strength, but it will decrease ductility. Okay, we also said this is GND density. We did a measurement on that using EBSD. We indeed observed the GND density in this layered structure. And we also said that this is a strain gradient. And like there's a positive strain gradient, like this, zero strain near at the boundary, more strain at the away from the interface. We did the measurement use high resolution digital image correlation. We found that the result is opposite to our concept here. Then we thought that all the dislocations are from the interface. And however, is that true or not? To verify that, we did a in situ TEM. We found that you still have dislocations, front-grid dislocation cells inside the larger grains. However, there's a dislocation density gradient. Okay, this was our in situ TM observation. The dislocation sources, front-grid sources are dynamically formed and destroyed after emission of field dislocations. There's a density gradient for front-grid sources, high density near the interface, which will give us this negative strain gradient. So there's no quantitative relationship between the GND gradient and the strain gradient because some of the dislocations got pushed into the boundary. The GNDs are not all there. So this makes the conventional gradient plasticity invalid. So they need to consider this. And it also shows that issue TM is important. Otherwise, you will not see it. Another observation we found is we look at all these different gradient heterostructure. This is layered structure. This is gradient. This is bimodal structure. You see that the deformation is always concentrated in some strain bands. They are not uniform. This is typical for all heterostructures. We still don't know what's the principle, what's the reason behind it. We have some hypotheses, but this needs to be further studied by our community. The biggest advantage of heterostructure material is it can be processed with current industrial facilities. It means easy to scale up in a low cost. Most of us here have been working on nanostructured titanium. We know how hard it is to scale them up. It's parallel at a low cost. And so this makes the commercialization
Professor Zhu, it seems you have...
functional material. I'm
okay.
finishing it.
No,
So
no.
this is one example for magnetic material. They also have a trade-off between magnetization and coercivity. And then when they use the heterostructure concept with hard magnet and soft magnet, they produce something similar structure. Okay. I also like to stress that there are international conferences in this area almost every year, several of them. So I hope more of our colleagues will join this new area. It's also a natural extension of our ultrafine granular materials. And I see Alex is working on gradient materials. That's actually one type of heterostructured materials. Thank you for your attention. I'm ready to answer your question.
Thank you for your report. I wanted to say that something wrong was with your internet connection. I didn't speak about the time limit, but anyway, thank you for your presentation. I want to ask our audience, what about question? I have a few not questions, just for discussion.
Sure.
In addition to beginning of your presentation about pollution and so on and so forth, it's rather actual problems, not problem situation for us as citizens of Magnitogorsk. And I want to invite you. I want you to invite us. I want to invite you to Magnitogorsk to visit our metallurgical plant, the biggest metallurgical plant in Russian Federation, and maybe it will be interesting for you.
Thank you for the invitation. I've never been there. I'll be happy to go there if there's an opportunity in the future.
Maybe our next conference for young researchers in our city will be a good chance for this.
Great, thank you.
And one discussion question. You demonstrated, or you have really interesting results, and you demonstrated a lot of advantages of HDI or hardening. But what about potential industrial application of such such methods based on these principles?
Well, that's the best part of this material. They are easy for commercialization for industrial production. That titanium we did, the way used ruling and partial recrystallization. In the ruling, that's an industrial process. Basically, if you go to a steel mill, they can use their current facility, just change their processing parameter. They can produce this material at an industrial scale. And we did some heterostructured dual phase steel. We presented it to a steel mill of what we did. They said, wow, that process, the processing cost may be even cheaper than your current process. And you get a better property and at a low cost, not higher or slightly higher than your current process. You can imagine the industrial application of this material.
Thank you. And do you have any plans about computer simulation of maybe multi-scale simulation, computer simulation of treatment of such materials? Because it will be really interesting from point of stress strain state during processing.
While I'm an experimentalist, so I cannot do those myself. I really would like, if any colleagues can do that, I'll be really happy to work with them and provide them with data and also tell them what are the critical issues we need. Basically, all these effects in structural, in metals and alloys are the really dislocation interaction with the zone boundary. How does that interaction occurs? How does this like material properties like stacking for the energy affect them? Those are the issues we need to study. And I think there's a lot of things can be done using MD simulation and other simulation methods. But I'd like to stress that there is there's a coupling between different zones, interaction between different zones. That's what gave us the superior mechanical property. And for magnetic materials, there's like this magnetic coupling. For us, it's mechanical coupling. Those effects has to be in the modeling, any modeling you do, if you want to calculate a mechanical property. Otherwise, you will miss the point.
Okay. Thank you.
Dmitry, may I have one question?
Yes, of course.
Yes, Ruslan.
Great talk. Thank you very much. It's nice progress. My question regarding some definition of structural materials. This is, of course, this mixture of ultra-fine grain structure and coarse grain. But what is typical fraction of small grains and high grains for titanium, for other materials?
That is a great question. Our experience is that the hard zone, the matrix, need to be like 70% or higher. The softer zone is between 20 or 30% so far. That gives us a better property. The reason is we want the softer zone to be totally constrained, surrounded by hard zone. Otherwise, the softer zone may link up with each other, may flow, may not be constrained. So that's why we want.
Okay, so 20–30%. This is from your experimental observation, or you have some calculation or something?
We have no calculation. That's from the material we have been working on. That's our experience, and we don't know. We don't have like a theoretical modeling on this yet. So there are a lot of modeling coming down on this. Why is that? I believe that fraction may also vary with other factors, which we do not know yet.
Interesting. In this case, one suggests. So if there are many ultrafine grains, so this material should be superplastic at some temperature. Have you tried? And maybe it will be.
No, we have not tried that. I don't know. Maybe it has. Maybe it may have some really interesting superplastic property. I don't think you can do that, right? And
okay.
Even Terry are experts on those.
And expect your answer on our paper also. Thank you very much. Yeah.
You're welcome.
So thank you. We should go to section with reports. Thank you, Professor Zhu. And next report from Professor Tan from Kyushu Institute of Technology, Japan. You're welcome.
Okay, thanks for the chairman for the introduction. I'm Yongpeng Tang from Kyushu Institute of Technology in Japan. Today I will give this talk in memory of the Professor ZHILYAEV. I first time met Professor ZHILYAEV in 2017 in Fukuoka and GSM, and also Professor ZHILYAEV, Langdon, Professor Zhu, Professor Kim participated in this workshop. Today, I want to talk about the magnesium alloy. Magnesium as the lightest alloy in the structural metallic materials are promising for application in the aerospace application. However, the practical application is limited due to the low mechanical strength and the low ignition temperature. Calcium addition has proved to effective to increase the strength and the ignition temperature. But as shown in the magnesium calcium phase diagram, the dissolution of the calcium in the magnesium only 1.34%. So for the casting magnesium alloys, if added amount of the calcium in the magnesium, a brittle or the intermediate compound were formed. So it became an issue to apply the intermediate compound to improve the strength and the ductility. Here, reports that the pure magnesium processed by ECAP. You can see with increase the ECAP passes, the tensile strength and the elongation, both of them improved. So with the grain refinement, the tensile strength and ductility is improved. For the severe plasticity process, it is widely used to enhance the mechanical property, not only due to the fabrication of the ultrafine grain structure, but also the refinement of the intermediate compound due to the cell strain. So in this study, we tried to enhance the strength and the ductility in non-flammable magnesium alloy through the grain refinement and the fine dispersion nanoparticles. In this study, we used the HPT process to fabricate the ultrafine microstructure. Here shows how to prepare the specimen for the analysis. We not only evaluate the mechanical property, including the hardness and the tensile strength, we also compare the ignition temperature and the electroconductivity before and after the HPT process. This is the process condition for the HPT process. We carried out the HPT process at two temperatures. One is the room temperature and the 300 Celsius. For the experimental alloy, we have two kind of content of calcium, 1% and 3%. So first, look at the S-cast microstructure with the laminar structure. This is a eutectic structure. The black is alpha magnesium. The bright contrast is aluminum rich and the calcium rich phase. First, look at the effect of the strengthening on the micro hardness. For the 3% calcium magnesium alloys, for the black line, this is as received. The sample hardness is about 75. After the HPT process, with the hardness, micro hardness is sufficiently high for the sample processed at the room temperature in the blue line and the red line and the 300 Celsius have a same level of the micro hardness around 100. So, and it is homogeneous across the disk diameter. We plot the micro hardness as a function of the equivalent strain. We found more than the equivalent strain, more than 200, with the micro hardness reached the saturation. This shows the stress curve of the 3% calcium magnesium alloys. You can see the black line is as received. The blue line is for the processed at the room temperature. For the red line is the processed at the 300 Celsius. First, for the as received sample have a low tensile strength, about 114 hectopascals, with the elongation is 5%. For the blue line processed at the room temperature, there is no elongation. But for the processed at the 300 Celsius, with increase the HPT revolution, from 1 to 1,000 or 100, the tensor strength and the elongation, both of them improved. After the HPT revolution for 100 revolution, we get the tensor strength about 400 megapars with the elongation is 5%. This is the result for the tensor result for the 1% calcium in the magnesium alloys. We get the similar result with the 3% calcium in the magnesium alloys. For the room temperature process at the HPT process, there is no elongation, but also with the high temperature at the 300 Celsius, with increase the HPT revolution, we get the high tensor strength and the elongation. After 100, can you hear me?
Yes, yes.
Okay. After 100 revolutions, we can get the tensor stress is about 314, and with an elongation around 12%. So we succeeded to fabricate the magnesium calcium alloy with high strength and high ductility using the HPT process at 300 Celsius. So to explain why we can improve the strength and the ductility, so first, we analyzed the crystal orientation using the EBSD analysis. We analyzed at the cross section at this position and found, and after the HPT process, we can get the cross section is the 1010 and 2110 orientation, and the average grain size is about 700 nanometer. And from the TM observation in the 2 revolution and 100 revolution, we confirm the grain size after 100 revolution is about 700 nanometer. And we also observed the nanoparticles with a size about 100 nanometer. To identify the nanoparticle, we analyze using XID analysis. The right finger is the enlarged over the left one. In the 3% calcium magnesium alloy, you can see there are 3 kinds of intermediate compounds. The first one is green one is Al2Ca. The second one is Mg Al2Ca. The third is Mg 2Ca. And compare with the 10 revolutions, after 100 revolutions, the intensity of the XID is increased. So it's meaning during the HPT process at 300 Celsius, the dynamical perception occurs. We also compare the microstructure using the element map by the STEM. This is 3% calcium in the magnesium after revolution for 10 revolution. And we found the homogeneous distribution of the mathematical compounds. After revolution for 100 revolution, we found the homogeneous distribution of the mathematical compound with the size of about 100 nanometer. From the EDX analysis, it is identified that the mathematical compound is the C36. And we also observed the nanoparticles using the high resolution TM. The left is Mg2 Ca. The right side is Al2Ca. Here we compare the electron conductivity before and after the HPT process. You can see for the blue one is for 1% calcium magnesium alloy, and for red one is 3 calcium in the magnesium alloy. For the 1% calcium have a high electroconductivity than the 3% calcium magnesium alloy, because for the 3% calcium magnesium alloy, there are 6% aluminum. So because the aluminum atom is dissolved in the magnesium alloy, so the electroconductivity is low, lower than the 1% calcium magnesium alloys. And after the baseline is after the HPT process, for the 3% calcium magnesium alloys, after HPT process, the electroconductivity is increased because during the HPT process, there are Al2Ca precipitates were formed. So the electroconductivity is increased. But for the 1% calcium magnesium alloys, due to the introduction of the strain during the HPT process, after the HPT process, the electroconductivity is decreased. Here is the result for the measurement or the integration after the before and after the HPT process. The real sample is before the HPT process. The open sample is the after HPT process. The square is for the 3% calcium in the magnesium alloy. The circle is for the 1% calcium in the magnesium alloy. You can see there is no HPT process have no effect on the decreasing of the ignition or the temperature. For the 3% calcium in the magnesium alloy have ignition temperature about 115 Celsius. For the 1% calcium magnesium alloy have the ignition temperature is about 900 Celsius. Finally, I give the conclusion. Not only the strength, but also the ductility is improved in the ultrafine 3 calcium magnesium alloy and 1% calcium magnesium alloy. Both alloy have a tensile strength more than 340 megapars with an elongation 5%. And the dynamic perception occurred during the HPT process at 300 Celsius. And the precipitate of the Al2Ca and the Mg2Ca within the ultrafine grain was responsible for the high strength and the high ductility. The HPT process have no effect on the ignition temperature of the 3% calcium magnesium alloy. The ignition temperature is 1015 Celsius, and the electroconductivity of the 3% calcium magnesium alloy is improved after the HPT process. That's all. Thank you.
Thank you for your report. That time is almost out, but colleagues, if you have any questions,
Can I ask a couple of questions? If you...
Of course, of course.
Yeah, first of all, if I'm not mistaken, at the beginning of the presentation, you focused mostly on aerospace application. But as I see, magnesium, calcium, zinc, and magnesium alloy could be used in medical application. In this case, the question, whether you try to measure corrosion resistance, something like that?
I measured the user. This one? I measured sorry, I didn't measure the electrical resistance. I measured the conductivity.
Okay. And the second one, did you try to measure mechanical properties in structure through time? I mean, did you measure stabilities, microstructure stability or mechanical property stability of these materials?
Okay. Sorry. Can you repeat again?
Did you try to measure microstructure stability and mechanical properties stability of such materials through time, or maybe after some thermal annealing?
Oh, okay, maybe.
Okay,
maybe we didn't measure.
So, colleagues, what about any questions? Okay, thank you for your presentation. We should go to the next report. Professor Yu from Central South University, China. Professor Yu, are you here? We have some participants from China with pure China nicknames, but I'm not sure that this is Professor Yu. I think no. So in this case, we should wait to 20 minutes. We have short break, coffee break, unplanned. But anyway, next report will be after 20 minutes from Sergei Mironov. Sergei, are you here?
Yes, I'm here.
Okay, we should wait 20 minutes for our schedule, and we will continue with your report. Okay.
Okay.
Thank you.
这个事情了。Hello, sorry, I forgot the time.
I'm glad to see you.
I went. Oh, sorry.
Okay, okay. Dima, this is Professor Yu.
I know. Nice to meet you. Maybe you can make your report in our coffee break after 7 report. What do you think? Professor Yu, what do you think? Maybe you can make your report in coffee break time, because we had coffee break now after 7th report. И ушел. А у него же актуальная версия программы, да?
Professor Yu, we have a time break, coffee break, but we can be without it because everybody can drink in a pause, and we have maybe from 11:40 till 12. Is it a time interesting for you? You can make presentation in that time from the beginning of 11:40. Is it okay for you?
Yeah, but yeah, I don't know the China time.
Oh, I can't. Maybe 11:40.
11:40. Okay.
Okay.
11:40.
Yes, we had coffee break now, and that's why we don't need the second coffee break, and that's why we can provide this time for your report. Is it comfortable for you?
Okay.
Okay, thank you.
Okay, thank you very much. Okay.
Sorry. How are you?
Sergey, are you here?
Yes, yes, I'm here.
So you can start. Thank you.
Okay. Okay. Let's put my presentation on the table.
It's okay.
Can you see my presentation?
Yes, yes, yes.
Very fine. Can you see my pointer?
Yes.
Just a moment. Okay. Good morning, dear colleagues. Thank you very much for your interest to my presentation. My name is Sergey, and the topic of my presentation is abnormal grain growth in friction stir welded aluminum. This work was a result of a joint activity of our research team, which includes Alex Kalinenko, Igor Vysotsky, Sergey Malafeev, myself, and Professor Rustam Kaybashev. Altogether, we represent the Laboratory of Mechanical Properties of Nanostructural Materials and Superalloys at Belgorod National Research University. Before I begin my presentation, I would like to emphasize that the title was a little bit changed. Title of my presentation was a little bit changed. So the current title of my presentation is Abnormal Grain Growth in Friction Stir Welded Aluminum. Okay. Friction stir welding is a relatively new solid-state joining technology. Its basic principle is very simple. For the welding process, a specially designed welded tool is used, which is shown here. Typically, this tool consists of two main parts, the larger shoulder and the smaller probe. The tool rotates with very high rotational rate, which may achieve several thousand rotations per minute, shown here. The rotating tool is inserted into the joint line, as shown here, and then translates along the line. Depending on particular conditions, the translation rate may achieve several 100 millimeters per second. Due to the friction between the rotating tool and the welding workpiece, the welded material is heated up to relatively high temperatures, as shown here. Accordingly, material softening occurs. The softening material of two welded plates is intermixed with each other, just producing a joint in the solid state. Due to the solid state character of the welding process, this technology avoids the formation of solidification structure in the weld zone and thus provides the production of sound welds with excellent mechanical properties, even in materials which are commonly believed to be unweldable, for instance, in aluminum alloys. As a result, friction stir welding has a great industrial potential. It is important to emphasize that the material subjected to the friction stir welding normally undergoes a very large strain at relatively high strain rate and elevated temperatures. So typical deformation conditions are colored red by here. So this combination of deformation conditions usually give rise to the dynamic recrystallization and thus leads to a drastic grain refinement in the stir zone. Accordingly, friction stir welding may also be used for production of fine granite structures. This technology is sometimes referenced as friction stir processing. Unfortunately, a significant drawback of the fine granite materials produced by friction stir welding is a relatively low stability against the abnormal grain growth. This undesirable process may essentially degrade material properties. Unfortunately, the mechanism of this phenomenon is still not clear. Attempting to get insight into this process we decided to measure crystallographic orientations of the abnormal coarse grains. Despite this idea is very simple, its practical realization is rather challenging. The problem is that the abnormal coarse grains often have very huge size, and thus the number of such grains available in a sample for the measurements is very limited. As a result, it is not so easy to get reliable statistics of measurements. In order to overcome this problem, partially at least, we decided to use electron backscatter diffraction technique and get EBSD maps from entire stir zone. Let's go to experimental section. So the material used in our work was a commercial purity aluminum alloy 1015. Is here. The material was supplied as 2 mm thick plates. The plates were friction stir welded at the tool travel speed of 600 millimeters per minute here, and the tool rotational rate of 2000 RPM. The welding tool was fabricated from a tool steel and consisted of a tool shoulder.
Это он сам показывает вот это еще все, да?
Having a diameter of 15 millimeters, 12 millimeters, sorry, and pin, threaded pin, having a diameter of 5 millimeters and the pin length of 1.7 millimeters. Following welding, the obtained material was annealed in the temperature range from 300 degrees C to 500 degrees C for the times of 10, 20, and 60 minutes. Microstructural observations here were performed by using electron backscatter diffraction technique. A composite EBSD map, which shows the microstructure produced in the transverse cross section of the friction stir welded material, is shown in this slide. The EBSD map was taken from entire stir zone. In this map, individual grains are colored according to their crystallographic orientations relative to the welding direction, and the orientation code triangle is given in the bottom left corner. It is here. An evident variation of preferential grain orientation is seen. You might see that color changes in some systematic way. This effect is well known in friction stir welding. It is well accepted that material flow during friction stir welding is mainly governed by the simple shear deformation, which is induced by a rotating tool. The crystallographic shear planes tend to align with the tool surface, and as the welding tool rotates, this gives rise to the very characteristic variation of texture in the stir zone. Orientation data were derived from 5 selected locations within the stir zone, 1, 2, 3, 4, 5, and we arranged as 111 and 110 pole figures, and shown in the bottom left of this, in the bottom part of this slide. To adjust the pole figures with the tool rotations, they were appropriately rotated, and applied rotations are also indicated in the bottom part of the pole figures. It's shown here. So it is seen that the developed textural patterns in all cases may be interpreted in the terms of B minus B simple shear texture. This was a quite expectable result because the formation of this type of texture during friction stir welding of aluminum alloys is typically reported in scientific literature. To get additional insight into the microstructure produced during friction stir welding, a series of high-resolution EBSD maps was taken from the material as shown here, location A, B, C, A, B, C. So the maps were taken from 3 different locations within the stir zone, which we will label it as A, B, and C. In all cases, the microstructure was dominated by nearly equivoxed grains with the mean grain size of around 1 micron. The measured fraction of high angle boundaries varied from approximately 60% to around 80%. This slide shows EBSD maps taken from the annealed specimens. Again, individual grains in the maps are colored according to their crystallographic orientations, and orientation code triangle is shown in the bottom left corner, is here. It is seen that the material annealed at 400 degrees C for 10 and 20 minutes, is here and here, experiences the abnormal grain growth. This process initiated either at the upper surface of the stir zone, shown here and here, or from the stir zone root, for example, here or here. It is important to emphasize that crystallographic orientations of the abnormal coarse grains very often distinctly different from those of the fine granite matrix. I don't know, for example, green colored matrix here, but brown colored abnormal grain is here. So the specimens are annealed for longer time, 60 minutes, or at higher temperature, 450 or 400 degrees C. The abnormal coarse grains consumed almost the entire stir zone. For simplicity, these all samples were referred as fully annealed specimens. Despite the entire stir zone was EBSD mapped in the annealed wells, the number of the abnormal coarse grains was still low in each particular specimen. So, to improve statistical reliability of our measurements, we combined all data taken from all fully annealed specimens in the single dataset. The schematic of the obtained virtual stir zone with 5 selected regions are shown here. The cumulative textural data were again arranged as 111, 110, and 112 pole figures, and shown in the bottom part of the slide. Is here. A very important conclusion which can be drawn from the pole figures is that the texture produced by the abnormal grain growth was not random. Instead, a distinct texture was seen in all cases. Moreover, the textural pattern can be described in terms of B minus B texture rotated at 30 degrees around 111 axis. It is illustrated here, and here, and here. To the best of our knowledge, the effect of the texture rotation associated with the abnormal grain growth has never been reported so far. So, origin of this phenomenon is completely unclear. On the other hand, the texture rotation is well known for recrystallization phenomenon. In this case, this effect is usually explained in terms of the so-called orientation growth mechanism. This mechanism can be explained as follows. In face-centered cubic metals, including aluminum alloys, the grain boundaries having misorientation close to 40 degrees rotation around 111 axis are known to be highly mobile. It might be suggested, therefore, that high mobility of these boundaries might provide some advance in growth of some selected grains at the beginning stage of grain growth. And this eventually led to the activation of the abnormal grain growth mechanism. So, in other words, it seems that the abnormal grain growth studied in this work may be explained in the terms of the orientation growth effect. Now let me formulate conclusion. In this work, the texture produced by abnormal grain growth in friction stir welded aluminum alloy was studied. EBSD measurements showed that the evolved textural pattern might be described in terms of B minus B simple shear texture rotated by approximately 30 degrees around axis 111. Based on this observation, it was supposed that the abnormal grain growth studied in this work can be explained in terms of the orientation growth mechanism. So this is all. Thank you very much for your attention. If you have any questions, please feel free to ask them.
Thank you, Sergey, for such an interesting report. Colleagues, do you have any questions? I have a few questions, but maybe it's a little bit newbie but anyway, on the slide where you demonstrate ninth slide where you demonstrate the scheme with zones 1, 2, 3, and 4 and 5. What happened between 9, по-моему, slide. Yes. What happened in the empty zones between 2 and 3 and 3 and 4?
In this case, the textural pattern, I think, is broadly similar to that shown in locations 1 to 5, but rotation angle is a little bit different. You may see that in all cases, the texture is actually the same. The different, only orientation of the pole figures is a little bit different. So we apply different rotations to align our pole figures with geometry of simple shear deformation imposed during friction stir welding. So I believe that if we get textural data from the empty regions and apply some appropriate rotations, we will get nearly the same picture.
And the second question, is it serious in homogeneity of mechanical properties or in for example, in the first and in the central zone? Regarding the size and the orientation of grains.
Mechanical properties. So this is aluminum alloy, and in this case, there is no big difference in mechanical properties, particularly in molecular hardness and tensile tests and something like this. But in some other materials, for example, in magnesium alloys, where texture effect is very significant, texture properties may be essentially different. In aluminum, there is no big difference.
Okay. And colleagues, do you have any questions?
Thank you for a very interesting presentation. And I have a question. When you speak about aluminum, you mean only the first series, or maybe others? That about that there are no differences in qualities, in mechanical qualities. It connected with only the first series or the higher series?
Friction stir welding might be applied in all types of aluminum alloys, and all types of aluminum alloys may be successfully welded. Also, unfortunately, the abnormal grain growth phenomena, which is studied in my work, is observed in all aluminum alloys, irrespective of series. So this is some global phenomena.
Thank you.
You're welcome.
So, colleagues, more questions? No. Okay. Thank you. We should go to the next report from Central South University, China. Professor Jin Li. Am I correct? Yeah, you're welcome.
Hello.
Hello.
Hello, my name is Li Jing. I come from Central South University, China. My advisor is Professor Yu Hainiang. It's my honor to be here, have this opportunity to give the presentation. Before I start my presentation, I have some words in memory of Professor Alexander ZHILYAEV. I still remember in 2019, Professor ZHILYAEV came to China and gave us a great speech. I still remember his wisdom and kindness, which deeply touched eyes. And I'm sure I will remember his spirit that will inspire the followers. Okay. My presentation is about gradient structure and cryogenic treatment. The title is Effects of Cryogenic Treatment on Gradient Structure, the column by cyclic skin path rolling. The main contents conclude three parts: background, cyclic skin path rolling, and the effects of cryogenic treatment. First, please let me introduce the background. As we all know, the development of high-performance materials is the everlasting research theme. Hall-Page formula reduced the relationship between microstructure size and yield strength. With the guidance of this formula, many severe plastic deformation technologies were investigated to refine microstructure size and increase materials strength. But the ductility and the strength show trade-off relationship in the conventional materials system. As Professor Zhu showed before, the banana curve means the trade-off between the ductility and the strength. With the increasement of material strength, the ductility drops dramatically. In order to overcome this trade-off relationship, the gradient structure was put forward. Gradient structure materials are typically designed with a gradient in the internal microstructure, such as grain size, twin thickness, and the laminar thickness. From a surface to the interior over a characteristic length scale, ranging from several nanometers to hundreds of micrometers or even millimeters. The fabrication methods of gradient structures, such as surface mechanical attrition treatment, SMAT, surface mechanical grading treatment, SMGT, rotation acceleration shoot panning, ISP, have the limitation of sample size and shape, which restrict the industry application. Cyclic skin path rolling, based on traditional rolling technology, can be an efficient way to fabricate gradient structure. I will introduce this CSPR in details later. The table shows some fabrication methods of gradient structure. All these methods can introduce gradient distributed pressure, strain, and strain rate, which can refine microstructure into a gradient distribution. From the table, we can see that the samples are relatively small, especially for these rotation deformation methods. Comparing with these methods, CSPR can produce large volume gradient structured materials. The next part, let's move to cyclic skin path rolling. This deformation method can fabricate gradient structure continuously, have a potential industry application. The left picture is the illustration of CSPR processing. The distinct character of CSPR is its reduction ratio. The reduction ratio should be kept enough small to concentrate the strain in the surface layer. The right picture shows the distribution of the pressure and the strain. By finite element simulation, we can see when the rolling reduction ratio is less than 1% per pass, the pressure and the strain only concentrated near the sample surface. The ratio of the thickness of the plastic string region to the thickness of the sheet is around 20%. The mechanical properties of CFPR aluminum samples and cold rolled CR samples are compared. From the engineering stress strain curve, we can find that the yield strength of CFPR process sheets have similar value with that of sheets subject to CR, which enhance greatly compared with the annealed sheets. However, compared with sheets produced by CR, the CFPR processed sheets have almost doubled fracture elongation, which means CFPR processed sheets have more desirable mechanical properties. TM was also carried out to analyze the mass structure of CFPR samples and CR samples. The calculation shows that during CR, the grain size in the surface layer and the core layer are almost the same. The plastic string in sheets is uniform, which is resulting in the same mass structure in the CR sheets. During CFPR, the plastic string only appears near the surface of the aluminum sheet, which resulted in much finer grain size near the sheet surface. As the grain size reduced to about 200 nanometers, the grains in the core layer retain undeformed about 2000 nanometers. Next part, I want to analyze the effects of cryogenic treatment on gradient structure economy by cyclic skin path rolling. The cryogenic treatment can help refine the mass structure, may increase the material's strength, or even increase material's strength and ductility continuously. In order to analyze the effects of cryogenic treatment, two groups of commercial pure economy were deformed by CFPR. One is operate at ambient temperature, marked as RT samples. The other were immersed into liquid nitrogen for 8 minutes before each rolling pass, marked as LNT samples. In the tensor engineering stress strain curve, the LNT samples show higher ultimate tensor stress and lower uniform elongation compared with RT samples. After annealing at different temperature, LNT samples kept higher stress and the elongation when similar with RT sample. LNT samples should higher thermal stability, but it's noticeable that after annealing at 150 degrees C, the tensor stress of RT samples had an increased trend. To study the inside of this phenomenon, high resolution TM was used. The original coarse grain sample showed almost non-dislocation exist. After CFPR, significant mass structure refinement and dislocation accumulation in both RT samples and LNT samples. Relatively, LNT samples showed more intense laminar structure, indicating higher dislocation density. The cryogenic treatment suppressed the dynamic recovery and promote the dislocation generation. After annealing at 150 degrees C for an hour, the LNT samples and RT samples showed different morphology. The dynamic recovery happened in the grain of RT sample. The low density dislocation area expanded towards laminar dislocation area. With low temperature annealing, the dislocation movements were thermally activated. The recent stress also released, accompanied with dynamic recovery, which may contribute to the tensor stress raising. In the LNT sample, twin exists stably, and the twin space was near 20 nanometers. Accompanied with dense stacking faults, nanoscale twins was induced in the LNT samples, showing stable mechanical properties, which contribute to the high thermal stability. The different morphology also indicate the different deformation mechanism. Some researchers investigated cryogenic deformed HCP structured materials, such as titanium and zirconium, and found that twinning is easier to be activated at cryogenic temperature. To the last two pictures, after annealing at 450 degrees C for an hour, the recrystallization was found in both RT sample and LNT sample. Large fraction of long dislocation, low dislocation density area was induced. On the one hand, dislocation annihilation and dislocation rearrangement occur concurrently during the recrystallization progress, which dramatically increased the fracture elongation. For both RT samples and LNT samples, the fracture elongation increased more than 30%. On the other hand, dislocation tangle was found in LNT sample. High density dislocation were induced in the cryogenic treated CSPR progress, which will not recover completely during relatively low temperature annealing. The unrecovered dislocation will contributed to the higher tensor strength of LNT samples compared with RT samples. The last part is the conclusions. From this research, we can draw conclusion as by deploying cryogenic treatment parallel to CSPR, gradient structure zirconium should higher tensor stress and slightly lower fracture elongation. The suppression of dynamic recovery and promotion of dislocation generation were the main reason for higher tensor stress. After annealing, the LNT samples showed better thermal stability because of synergetic effect of stable large-scale twins and uncompleted recovery. Thank you for your attention.
Thank you for your report. Colleagues, do you have any questions?
May I ask one question?
Please.
Thank you for interesting presentation. And I want to ask you about perspective of industrial using. What are the problems which are constrained in the way to use it in industrial, or maybe no constraints? What are the perspectives?
As far as I know, the control of the reduction ratio is hard to manage in the industry application. The FEM simulation also shows that when reduction ratio increased to about 2% per pass, the string come across all the sheet in the sequence. So I guess in the industrial application, this string distribution will can't create gradient structure we want. Thank you for your question.
And one more question, if it's possible. You enrolling, you have 1%, not more than 1% in every pass. And but what is the limitation of why do you not increase the reduction? The temperature, are you afraid the temperature is growing in this process or not?
That's a great question. I think there are two reasons. The first one is the string distribution. As I told before, in the last question, when the reduction ratio is enough small, the string can concentrate it in the surface layer. The second one is the heat reason in the definition. When reduction is enough small, the heat will not reason. We have do some FEM simulation showed that when the reduction ratio is enough small, the heat the temperature reason would be less than 20 degrees. Thank you.
Thank you.
A few questions from me, newbie in these old technologies. What, in addition to question of Professor Pesin, what are size limitation for such processes? For example, what is the biggest and the smallest size of sheet you can produce by clear rolling, for example?
You mean the size restriction of CFTR compared with the other gradient structure manufacture methods?
In comparison with traditional rolling, for example.
Yeah, okay, I show the page. Yeah, in here. We can see in SMT, SMGT, or IESP, the same size are relatively small, especially for rotation deformation methods. This IESP. The stress induced in this method restrict its same size. The IESP based on rolling technology, it can produce gradient structure materials continuously. So I guess it had better industrial application.
And also one question about, do you have some kind of thermal residual stresses during this treatment due to serious difference of temperatures of initial billet and final product?
Yeah, I tried to analyze the residual stress before, but sorry, I do not have the result for now. I think I should carry this study in the future.
I hope
thank you.
we will see it soon.
Yeah.
So thank you for your report. Colleagues, we should go to the next report.
Thank you.
Thank you. From Dmitry Gunderov. Are you here, Dmitry? Dmitry. So we don't have Dmitry in our chat, but we have Professor Yu maybe. Professor Yu, are you here?
Yes.
So I think you can fill this gap in shadow. You're welcome. If you want, of course.
Yes, thank you. I'm sorry for the missed time. My name is Haiyan Yu, and now I'm working at Central South University. I want to introduce the high performance element laws by using chloroforming. And the main contents include 4 parts, and this picture shows ZHILYAEV and PACE, which is my university. And I should maybe use this one. In the world, the first rolling mill was established about 240 years before, and until now, the people could use hot rolling, wine rolling, cold rolling. And co-uranium is only about 10 years. So I think this is a new technology, and then we can make some new knowledge in the future. And for the aluminum subject to severe plastic deformation, when the equivalent strain large a certain value, the hardness will reduce. But we think the co-uranium can solve the problem. And people think the occurrence of plastic deformation at a room temperature for most metals relies on the movement of dislocation. And so people think the pore ductility is expected for most metals test at a constant temperature, like the tin. In tin alloys, the curve appears with a low temperature. But for aluminum alloys, it turns the opposite. We found that the aluminum alloys have excellent ductility at constant temperature, and we can test the tensor experience in the conventional environment in my lab. And this picture shows the mechanical property of all 61 alloys and tested at a constant temperature. Figure A shows the engineering stress and strain curves of etched aluminum alloys with reduction ratio. We could find in this picture the sample test at a constant temperature show high strength and high elongation compared to that at a room temperature. And in B, C, D, we also could find the UTS or some subject to constant temperature are higher than that at a room temperature. And we compare the difference of UTS in room temperature and constant temperature. We find that a large difference when the unit reduction is only 50%. The difference of UTS reach about 51 ampere. With the increase the unit reduction ratio, the difference of UTS gradually reduce, and also the elongation difference reduce with the unit reduction ratio. And this picture shows the ferrous surface of aluminum alloys and tested at a room temperature and a constant temperature. And A, B, C for the samples tested at a room temperature, and D, E, F and tested at a constant temperature. From this picture, we could find the sample tested at a constant temperature show much deep dimples, and this means the improvement of elongation ductility at the constant temperature. And this picture shows the elongation ratio of different aluminum alloys at the constant temperature. We could find for most of aluminum alloys, the elongation gradually increase with reduced temperature, except 5 or 8 6 alloys. And by this alloy, at first, the elongation ratio increase when the temperature is 120 K, the elongation reduce. So we think for most of aluminum alloys, the elongation ratio at a high temperature is much high, at a room temperature is low, but at a constant temperature is high again. It's a typical V shape. And for the co-uranium, I think that this is the most common conforming techniques, because we may be used in the South Atlantic and moons in the future to continue manufacture in the future. We tested the grain size for compared to the room temperature and constant temperature. We use the HM uranium at the room temperature. We could get the grain size about 500 nanometers. We use HM co-uranium. The grain size can be refined to 210 nanometers. And we compare the grain size of two different SPD techniques. And the HV coronium is similar to other well plastic techniques. We compare the grain size subject to continue LB, and in this figure A and figure B and show similar grain size about the 460 nanometer. We use LB and coronium after through the LB and 2 pass coronium, the mean grain size can reduce to 200 nanometer, 290 nanometer. Also, the engineering stress is the highest. We studied the macrostructural erosion of LB aluminum sheets and during submarine uranium. When used something called uranium, the grain size can be reduced from 600 nanometer to about 350 nanometer. When you use something coronium, the grain size can be refined to 260 nanometer. We studied the mechanical property of LB processor sheets and LB plus coronium and aging. We found when you use the coronium plus aging, the elongation rate and the UTS can be improved. We studied the focus space. One A is LB processor symbols, and D is LB plus coronium and plus aging. It shows much more dimples. It means the improvement of ductility of the sheets. And we studied the precision of the aluminum during aging. We could find it, and for HV corrode symbols, the precision is different with the other symbols. And then we studied the superplasticity behavior of all 6 at 3 sheets subject to coronium and coronium. In the upper figure shows when you use the room temperature uranium and -100 uranium, the elongation rate is this is the 2 lengths. When you use the -190 coronium symbols, the elongation rate can be doubled. And these 2 figures shows the SEM figures of focus space. And we also studied the variable behavior of UFD materials. For most samples, the variable behavior is 45 degree. Some samples is 90 degree. However, we find for the corrode sheets, the shear failure angle and when go to 60 degree, it become uniform. We also use the fluid element to validate our results. And also we studied the grain size near the surface of all at 3 sheets out of tensor fracture. We found that the mean grain size of the grain size of the tensor stress reach the minimum grain size of SPD at the room temperature. And so we found that when for the aluminum alloys, the grain size reach the maximum grain size at the room temperature, they become fracture. And when they are relevant to a small grain size at the constant temperature, so they are could improve the elongation. And also we find that they use the low temperature aging could improve the ductility and strength of CSO1 alloy sheets. Only 100 degree aging, the elongation rate improve greatly. And also we studied the aluminum composition alloy sheets while corroding and during aging. We studied the grain size, and one uses the corroding, the going is much finer. And for an original alloys, we should use the edge temperature about the 160 degrees. And however, when you use the corroded sheets, the edge temperature can be reduced to 80 degrees, so the edge temperature can be reduced greatly. And we could save the energy in the future, and also improve the mechanical property. We could compare the weak hardness A and D. And also we studied the mechanical property of aluminum copper lithium alloy sheets to a variety of coefficient temperature. We find when the sheets start to minus 100 degrees, and the strength and the integration is high, then that start to minus 190 degrees corroding and hot corroding. We studied the microstructure. We find that in figure D there maybe appear the heat corrosion and microstructure. And we studied the aluminum titanium laminates while corroding. We also found minus 100 degrees so highest peeling strength. This is interesting because people generally we think the bonding strength may be reduced with a low temperature, but always show different phenomena. And also we find that the corroding could reduce the edging cracks and during laminar rolling. From A, B, C, 1, and there appear edge cracks start to cold rolling. And when you use corroding, we don't find the edge cracks. And also we studied the aluminum copper laminates while corroding. We also find and when you use corroding at a minus 100 degrees, they somehow show highest strength and best integration ratio. And we also found that there are some jaggeds near the interface between the copper and the aluminum lamina interface. So this may be improve the bonding strength and also mechanical property. And there are some other kind of performance techniques such as cold-rolling, cold-stamping, cold-machine, and cold-forging and cold-extrusion. And when you use cold-rolling, we could improve the rolling depth. When you use cold-stamping, we could improve the surface quality. When you use the cold-machine, we could improve the surface life of machines. And also cold-forging and cold-extrusion could improve the mechanical of some of products. And just is the going size subject to different forming technologies and at a room temperature and cold temperature. We could find for most of aluminum alloys subject to cold forming, the going size can be much finer compared to at a room temperature. And also we studied the UTS of aluminum samples start to RT forming and forming. And the UTS start to forming improved greatly and compared to the in RT forming. And now I want to make a short conclusion. And some kinds of metals have excellent mechanical properties at constant temperature compared with the at room temperature. And corroding can improve the mechanical property of aluminum laminar composites, and also conforming may be used to develop new metals and composites in the future. And thank you for your attention. Thank you.
Oh, thank you for your report. Colleagues, we have a lot of specialists in chat in Creo rolling. You can ask your question.
May I ask one question?
Yes.
Thank you very much for your presentation. And I want to ask you about the difference between the temperature of the sheet before the rolling and immediately after it. What is the increasing of the temperature for one pass?
And we use the friend element method to calculate the increase of sheets of temperature during corrosion. And during the increase of when the uranium tension is less than 30%, the temperature about 40 degrees. So when you use minus 190 degrees and the thermal increase of the 40 degrees, the sheets of the uranium should be minus 115 degrees. So it's still at a virgin temperature.
Oh, thank you.
Can I ask a small question?
Yeah.
It's just to clarify, maybe I wasn't too okay. At the beginning, when you described the experiment, I unfortunately didn't catch it. Did you put just the sample in? Did you put temperature, cryogenic temperature only for sample before rolling, or maybe your rolling shaft is also cooled by?
Yes. No, we only pour the samples before rolling and in a cryogenic box. So we put the kind of temperature of minus 100 degrees, minus 150 degrees. We could use the machine to control the sample temperature. And during rolling, we want to use the liquid nitrogen to cool down the work roller. So we could keep the low temperature in the future.
Okay, and general questions. Whether you try your experiments with HCP materials, I mean magnesium, titanium, zinc, or something like that, or just aluminum?
Sorry.
It's okay, I mean, whether you try your experiment, your equipment for HCP materials, magnesium alloys, titanium, something like that, or was all of them, or well, all of them were spoiled?
Yeah, we want to study the magnesium alloys, but we find for aluminum and copper and titanium are good for corrosion, but for magnesium alloys, the toxicity is not high, so it's difficult to carry out the corrosion. But we want to develop some special magnesium alloys that can be used to corrosion in the future. So I let one PhD students to study to develop some special magnesium alloys to make it can be used at a corrosion temperature in the future.
Okay, thank you for your presentation and for your answering.
And also one question from neighbor field. Okay, let it be traditional rolling mill. But how can I prepare traditional rolling mill for cryo rolling?
Sorry.
What should I change to in traditional rolling mill for cryo rolling? Lubricant, surface of rolls, something else. From point of equipment.
Yes, and I think because we could make the rolling mill as a small box, like a box. So use the liquid nitrogen gas to cool down the rolling mills. Yeah, make the rolling mill in the box and then cool down the temperature of the box. So the rolling mill, all the temperature all cooled.
Okay, thank you. So thank you for your report. I see Dmitry Gunderov here. I think I can provide you our coffee break time for your report, if it is comfortable for you. Дмитрий, мы вас не слышим. Так, сейчас слышим. Поскольку мы должны идти согласно расписанию, можно перенести ваш доклад на время кофе-брейка? Тогда мы просто на кофе-брейк не пойдем, а послушаем вас. Вас это устроит? С 11:40 до 12.
А почему? У меня же по присланному расписанию у меня сейчас доклад. 11.
В 10:40 был.
Ну, я не знаю, та программа, которая у меня сейчас на руках.
Она поменялась.
Ну, уважаемые коллеги, надо рассылать актуальные программы. И вообще надо людям присылать программы, потому что, например, ну, Шереметьев просто не знал, что он включен в доклады и что у него доклад. Никто не прислал. Я тоже случайно. Ну, давайте, когда скажете.
Так, в 11:40 вам будет удобно?
Ладно, удобно.
Спасибо.
Спасибо.
Now we have report from Irene ZHILYAEV from University of Padova, Italy. You're welcome. We don't hear you.
Claudio?
Oh, it's okay.
Okay, can you hear me?
Yes, yes, yes.
Presentazione dall'inizio. Good morning to everybody. First of all, thank you very much for the opportunity. As I was in Magnitogorsk several times, I hope to come again. My presentation concerns the electrically enhanced plastic deformation of duplex stainless steel 2705. It is this project is a joint between our colleague in the University of Padova, mechanical and electrical engineering, and Professor ZHILYAEV from the Mechanical Engineering Research Institute of the Russian Academy of Science. Yesterday, he spoke about the general features of the electroplasticity, and today I will present a specific application. Just a few words concerning duplex stainless steels. Duplex stainless steel are biphasic steels with a ferritic and austenitic phase with about 50% one and 50% the second. The best mechanical and corrosion resistant properties are achieved for almost equal fraction of the phases. This equal fraction of the phases is the result of an accurate balance of chemical composition and post-forming and an annealing treatment. These steels are high alloy steels with chromium in the range between 20 and 27%, nickel between 1 and 9%, molybdenum less than 4%, and other elements like nitrogen, manganese, copper, and tungsten are added for tailoring specific properties. All these steels have a very low carbon content, less than 0.3%. These steels have some positive and also negative aspects. The issues they are sensitive to diffusive and also non-diffusive solid state transformation. Especially in a temperature range between 400 and 900 degrees. This temperature can be reached during the cooling after annealing, or for example, during the welding. Other solid state transformation that sometimes is detected in this steel is the strain-induced martensite during the cold plastic deformation. All these phase transformation can affect the mechanical property with a strong reduction of the toughness and the loss in corrosion resistance. As a consequence of this phase transformation, there are some limitations in the service temperature of the steel, which can be defined between -50 and 250 degrees. Another implication is in the limitation of the maximum quenchable cross section due to the cooling rate and welding operation. Okay, why electroplastic effect? Electroplastic electrically assisted manufacturing called AEM, which utilize the electric current flow to assist in metal forming, has become a promising and challenging method since the last century. The first studies were performed by Macklin and Torisky of the Academy of Science in Moscow, and recently there was a big effort in applying this method and in trying to understand the basic, the physical basic and the explanation of this phenomenon. Nowadays we have a project in cooperation with the colleague ZHILYAEV, because there is a lack of there is no consensus on the regarding the fundamental mechanism behind the electroplasticity. Some researchers argue that the Joule heating plays a dominant role, while other believes that there is an electron wind force which create an interaction between the dislocation and the electrons. Another theory is based on heterogeneous localized Joule heating. There is a very recent work confirming that the localized heating on the grain boundary could be the explanation of this phenomena. Another one elaborated 2 years ago concerns the excess of electrons in the nearby the dislocation, and another theory speaks about the effect of localized magnetic field. We did a lot of tests on different materials, and right now we are quite sure that the staking fault energy, for example, affect the electroplasticity. Generally, we have found that higher the stacking fold energy, higher is the electroplasticity effect. So, as the duplex stainless steels are biphasic steel with ferrite and austenite, and as the austenitic phase as the low is the phase with the lower stacking fold energy, it is very interesting to investigate the influence of a continuous and pulsed current during uniaxial tensile test with a material which possess two phases with different crystal structure, a BCC ferrite and FCC austenite with a different stacking fold. As has been observed that materials with electroplasticity has been observed to influence more the material with BCC phase. The steels is this is the chemical composition. It is a standard standard one. The experimental, we used a commercial MTS with 50 kilonewton. It was self-made, adapted for electrically assisted tensile testing with the copper jaws. The power supply is about 60 kilowatt maximum power at 10 volts and 6,000 current, 6,000 ampere current. To measure the temperature, an infrared camera was used because in our mind it is important to separate the thermal and non-thermal effect. The experiments were performed with continuous electrical current from 5 to 15 ampere per square meter and pulsed current from 50 to 250 ampere per square meters. This limitation is due to the maximum temperature that the steel can achieve in order to avoid the phase transformation. As a received material was a duplex stainless steel plate, 2 millimeters thickness, hot rolled with the last pass performed by Ormin. The materials, the material was provided by Outokumpu. Here, a macro image of the sheets with a very marked texture due to the rolling process. The ferrite and austenite volume fraction were determined by optical microscope with an image analysis and with red diffraction with reticle correction. Here we can see the peaks of the austenite and the ferrite, and the volume fraction was about 50% ferrite and 50% austenite. So this steel is really well balanced. The geometry of the specimen is reported here. The specimen were obtained across the rolling the direction in order to obtain more contribution of phase boundaries during the formation, because there are some theory concerning the heating and the effects of the grain boundaries on the current distribution. As regards the ZHILYAEV, as I said you before, this steel is very sensitive to solid phase transformation at temperatures above 500 degrees. So, for the continuous current, it is possible to use the current from 5 to 15 ampere per square meter, and here the maximum temperature reached. While for the pulsed current, it is possible to achieve very high current density, maintaining the same maximum temperature. On the picture, the same data are reported. So the experiments were performed with these current densities. As regards the result, Joule heating, during the tensile test, due to the reduction of the size, here I reported the current density evolution with the peak of temperature in correspondence of the fracture surface. This is the real temperature that must take in account. By comparing the results in continuous and thermal regime, it is evident that on the left, I reported the continuous current stress and strain. Baseline means room temperature. On the right, the same curves, but they were performed without current. In both cases, it is an evident decrease of fracture strain, yield stress, ultimate strength, and uniform elongation were detected as at increasing the temperature with no current and current. At higher temperature, the dynamic strain edging has been detected. Going to the tensile tests in pulsed current, the pulsed current regime is really more interesting. The the first curve is the curve obtained at room temperature and without current. The others are related to 50 ampere per square meter, 100 and so on. The serration of the flow stress curves are related to the electrical process. Here it is evident that the fractal strain is comparable to the room temperature test, despite the thermal regime. Another result is that the flow stress is lower than the one obtained at room temperature. And unfortunately, no special trend with respect to the electrical current density. Here from 100 to 250 ampere per square meters, there are not many differences. Also, in the tensile test in pulsed Kunder regime, the dynamic strain aging has been detected at the highest current density. But if we zoom the curves, we can see that for the lowest current density, there is nothing special. But going to the second curve concerning 100 ampere per square meters, it seems that like an annealing, a recovery with the lowering of the strength after each pulse. Continuing with the 150 ampere per square meters, this difference seems to increase at 200 ampere per square meters. The difference is 5 megapascal, and at the last one, the highest current density, the effect seems to decrease. Right now, we don't have a specific explanation. We suppose that as the temperature increases, the thermal effect can overcome the effect of the current. But
Professor Kaleri, excuse me, time is a little bit out.
Okay.
We can provide about 1 minute, for example.
Okay. Relative uniform strain is the real interesting parameter. Relative uniform strain has been calculated in comparison to the baseline one, and it is evident that with the pulse and current, the increase in relative the decrease in relative uniform strain is the maximum. We found an increase in uniform elongation for the partial test. The fractal strain is comparable. The ultimate strength and yield strength are not affected. an uneven distribution of the electrical current through the material, so the higher contribution of the staking fold, higher staking fold phase, and a localized hotspot in correspondence of the phase boundary. Thank you very much for the attention. And this is a picture of. Okay, sorry for the delay.
Everything is okay, colleagues. One question, one short question, if you have something. Okay, Professor Pesin. No. Okay, one question about slide number 9. About
number 9.
About orientation. According to data, at the initial state, you have rather serious grain orientation. Did you research the influence of initial texture or grain orientation for the next process?
No, we didn't test yet. We did all the experiment along the same direction, but.
Okay. So thank you. We must go to the next report. Thank you for your report. Anna Churakova.
Yes, I hear, but unfortunately, I don't have the opportunity to turn off the video.
What?
You can okay without video.
Yeah.
So we see your presentation.
Yes, okay. Good afternoon, dear participant of this conference. I would like to present to your attention a report on the topic, the study of multiple martensitic transformation in titanium nickel alloys of different composition. Just a minute. Now, titanium nickel alloys are functional materials that undergo martensitic transformation, which are diffusion free-phase transition of the first order with cooperative displacement of atom during the reagent on one crystal lattice into other, and in the case of titanium nickel alloys, upon cooling from austenite B2 lattice with BCC lattice to a martensitic monoclinic distilled orthorhombic lattice B19. The table you can see lattice parameters of titanium nickel alloys. Also, titanium nickel alloys are functional materials with characteristic shape memory effect and super elasticity, and are widely used in medicine and technology. Under operating conditions, a device made of titanium nickel alloys undergo thermal and mechanical cycling, and thermal cycling is one of the ways to improve the properties. In this regard, a large number of studies on this slide, you can see a scheme of generation dislocation on existing defects. In this work, this result. Thermal cycling is multiple heat cycles in the temperature range of martensitic transformation B2, B19. It is known that thermal cycling on these alloys is possible changing shape memory effects parameters changing the stages of transformations, accumulation of reversible deformation, and other influence. In this work, purpose analysis of effect thermal cycling through the temperatures of monazite transformation on titanium nickel alloys in various structural states and in various composition. As alloys materials study selected one of equiatomic alloy and second with high content of nickel. The slide presents a diagram of titanium nickel system alloys and microstructure and characteristics of titanium nickel in initial state. To obtain the ultrafine grain structure, we used the ECP method according to the mode shown on the slide. The nanocrystalline structure was formed by high pressure torsion and subsequent annealing at temperature 350 degrees Celsius. And the technique of thermal cycling on titanium nickel alloys is consisted of rapid cooling to temperature of liquid nitrogen, holding and rapid heating to 150 degrees Celsius, which is higher than the temperature of a reverse monazite transformation. Result on this work. In the coarse grain state, titanium nickel equiatomic alloy of titanium nickel has a grain size of about 200 microns. This picture you can see on previous slide. According to term data, the structure is predominantly martensite. You can see these twins of martensite formed during monazite transformation to accommodate internal stresses with plates with which 1850 nanometers. After thermocycling with the maximum number of cycles, 100 cycles, the width of martensite plates decreases to 60 nanometers. In addition, the formation of composite nanotwins 001 B90 with plate width of 10 nanometers is observed on this picture. The formation of nanotwins and degrees of the width of the martensite plates are probably associated with accumulation of dislocations during martensite transformation. In the ultrafine grain state, the grain size can be estimated by size of initial austenite grain equal 600 nanometers, inside which twins each equal 18 nanometers. From the data presented in the table, it can be seen that the width of martensiting plates in ultrafine grain and coarse grain state decreases, and in the ultrafine grain state, the decrease is more intense. As a result of a thermocycling with 100 cycles, the width of the plates decreases almost, and nanotwins with several nanometers also appear. After HPT, the structure in this alloy has an amorphous crystalline character. Annealing at 350 degrees Celsius leads to complete crystallization of the amorphous phase and the formation of a nanocrystalline structure with a grain size of about 35 nanometers. After thermocycling in 100 cycles, no change in grain size is observed, but compound nanotwins can be found inside some nanograins. You can see in this picture. X-ray structural analysis at different temperature when at room temperature and 150 temperature when the materials is in the austenitic state showed that as a result of thermocycling in the material, there is an increase in internal microstresses, a decrease in coherent scatter region accompanied by increases of dislocation density. This character of dependence is observed in all studies states. However, the difference in degrees in the dislocation density after thermocycling in coarse grain and ultrafine grain state is less than the error of the XRD method. In this slide, you can see DC results in this alloy. In both states, in the alloy, the direction of temperature changes during the thermocycling process. First, with an increase in the number of cycles, the temperature decrease and then increase. The coarse grain state is characterized by a more significant shift in transformation temperatures with a gradual recovery to the initial values. In ultrafine grain state, the dependence is smooth and the temperatures are more stable. And we can carry out mechanical properties on small samples. The slide shows data of mechanical properties in this alloy. As a result of the thermocycling in the coarse grain and ultrafine grain state, an increase in the yield stress according with phase hardening occurs, and in the ultrafine grain state, the increase in the yield stress is greater than in the coarse grain state. In addition, there is an increase in the values of phase yield stress and estimate reactive stress. Microhardness also increases in the all studying states. We observe great increase in the yield stress indicate a greater phase hardening in the ultrafine grain state. Similar studies on an alloy with high nickel content having an austenitic structure showed that as a result of thermal cycling, the dislocation density also increases. In the ultrafine grain state, a sequent decrease in the size of structure elements is observed. The formation due to the formation of dislocation walls. After thermal cycling, nanotwins 1001 type are formed in nanocrystalline states. You can see this X-ray analysis data with result similar equiatomic alloy. Also, we can mechanical properties on this alloy show the increase yield stress in above states and increase microhardness in coarse gray and ultrafine grain states also. This slide presents the main result on this work. Thank you for your attention.
Thank you, Anna, for your report. Colleagues, so do you have any questions? Okay, one small question from me. Anna, could you ask what is potential application of these materials in UFG state?
This state on this result shows that thermocycling in ultrafine grain states is more increases of mechanical properties, microhardness, and we can carry out studies on the stability of the structure in other alloys, and this result shows that ultrafine grain state is maybe more stability after many thermal cycling cycles.
Okay, thank you. So thank you for your report, and we're going to report from Dmitry Gunderov. You're welcome.
Yes, my presentation. Так, сначала.
Yes, we see.
Yes, it is my presentation. Let's slide. Yes, I know Alexander ZHILYAEV since 1990. I was student of Bashkir State University, and he working young scientist in Bashkir State University. And some times later, you can see presentation of Valery Danielenko. He know Alexander from 1966 because he taught with him in Bashkir State University. You can maybe interesting lecture of Danilenko too. And now I ask my colleague Vasily Astanin and present my presentation. Begin.
Good day. High pressure torsion is well-known deformation pattern. You can see that according to the well-known formula, very high shear deformation are achieved during deformation. Currently, the Web of Science features over 4,000 of articles on the topic of such deformation. But as it was shown earlier in my speech yesterday, we proposed a scheme for determining slippage during high-pressure torsion process. A disc is taken, cut, the place of cut is polished and covered with lacquer, and then both halves are inserted into high-pressure torsion tooling, and a certain number of revolutions are made. We can see that copper has undergone significant deformation, while a hard material, such as metallic glass based on zirconium, hardly deforms. It is possible to roughly estimate what shear deformation occurs in the bulk metallic glass sample after 5 revolutions of the anvils. And we see that by the shift of the upper side relative to the lower one, we have a deformation of about 1.5. According to the formula, it should be 150. Considering the absence of torsion of bulk metallic glass, there is other works indicated on the slide. We also tried to estimate the shear deformation that is realized when ordinary metals are torsioned. For example, we can see that if we take the initial nickel cut and apply our scheme, then the sample undergoes a noticeable shear deformation, although it's slightly less than expected compared to the copper. Then we did the following experiment. We gave the nickel sample 5 turns, cut it, varnish the ends again, insert it into the rig, and again made a quarter turn. And we see that after such a deformation scheme, the sample previously subjected to 5 revolutions when we make another quarter of revolution, shear deformation is not realized. This is the result of the known slippage effect. It is an important topic, but not all reviews are fully covering it. When we torsion soft metals, the torsion is mostly successful. For example, when we subject the copper to the first 5 turns and then for another quarter turn, noticeable deformation occurs, especially at the edges. When we subject the aluminum to 5 turns, then cut to the sample and make 1 quarter turn again, the deformation is realized almost completely, even if it was not even possible to separate the halves of the sample due to sticking, even through the ends were varnished with lacquer. But on hard and hardenable materials, on low carbon steel or nickel, if we twist the original sample, we see a noticeable shear deformation. If we first make 5 revolutions, then cut sample and subject to the joint high pressure torsion for a quarter turn, then we see that deformation is not realized. At the same time, if we look at the structure of the sample subjected to 5 revolution torsions in our setup, we will see that the rather fine structure has formed, the same that it was seen by other authors, with a grain size of about 100 nanometers. That is, hard materials, after reaching a certain strain, stop deforming. In soft materials, torsional deformation is realized in this case, but nevertheless, in hard materials, the structure is also refined. What causes the sample to torsion? Due to the fact that the friction force of the sample surface is greater than the yield stress of the sample. In most work, we indicate the pressure during high pressure torsion is equal to 6 gigapascal. However, for the calculation, we take the working area of the anvils. But in the contact zone during torsion, the area is actually larger since there is a flash around the sample. If we take into account the total area of the contact zone during high pressure torsion and apply the loads that we use to achieve our pressure, then we see that the pressure is actually 3.5 gigapascal. If we take a friction coefficient equal to 0.4, then the result is a frictional stress of about 1.4 gigapascal. This is significantly higher than the yield strength of the copper, and therefore copper undergoes deformation. But for example, for deformation of BNG or steel after 5 revolutions, it's not enough, and deformation is much less. Accordingly, torsion cannot be realized. But at the same time, we know that with an increase in the number of revolutions, our structure becomes more and more refined, even in hard materials such as steel. However, how this can be realized? We assumed this approach. Due to the looseness of the machine and the inaccuracy of the shape of the anvils, the upper anvil may deviate from the axis. We took the deviation, this deviation angle equal to 1 degree. We carried out a simulation in deformed 3D. Deformation as a result occurs with such scheme due to the deviation of the upper anvil by 1 degree relative to the lower anvil. According to our calculation, this is fairly high deformation of 3 at 5 revolutions. In fact, the possibility of such mechanisms, the deviation of the trackers from each other, was already mentioned at this conference yesterday in the report of Roman Kulagin. We need to somehow avoid the slippage effect, and we know that there is a well-known method, accumulation rolling, in which after each pass the billets are folded and rolled again. We have proposed a similar scheme, accumulating torsional deformation under high pressure. First, we make 1 revolution of the high-pressure torsion, then the sample is cut into several parts. These parts are stacked on the anvils. Pressure is applied. As a result, the entire stack is flattened, and the torsion is repeated again. Thus, the operation can be repeated several times. The cycle of cutting, compression, and again high-pressure torsion deformation. In the final stage, a large number of revolutions can be performed in order to consolidate the sample due to large deformation. In the same way, you can consolidate tapes, powders into fairly monolithic samples. The total number of revolutions is 10, but due to the cycles of deformation of compression and torsion, it is possible to achieve a significantly higher grade, higher strain. We investigated the effect of accumulating high-pressure torsion on steel with 0.1% carbon. We see that distribution of micro-hardness after accumulative deformation is noticeably higher than the after usual high-pressure torsion scheme for the same number of revolutions, and the structure is refined noticeably more. In this case, to 50 nanometers. This shows the effectiveness of the scheme. We also investigated the effect of the accumulating high-pressure torsion on stainless steel. While we see a stronger phase transformation, it is known that in the steel, high-pressure torsion leads to the transformation from the gamma phase to the alpha phase. After 10 revolutions, the content of the alpha phase is small, and after accumulative high-pressure torsion, the main peak of the alpha phase becomes significantly higher than the gamma one. That is, the amount of the alpha phase has increased significantly due to strong deformation that we achieve with accumulating high-pressure torsion. So that's all. Question, please. Thank you.
So, thank you for your report. And in addition to previous question from yesterday about computer simulation to you. About computer simulation. In central zone, you have some kind of small deformation. But did you find this zone in your real samples, in your physical modeling?
Really, at high pressure torsion, really some in center, no big deformation. in the real samples also. It is a result of simulation and result of simulation for this processing for torsion with low angle and for traditional torsion. Also, we see some in center zone low deformation zone of samples.
And also, did you try to make some kind of multi-scale simulation to observe changes on micro level, stress, strain, state on micro level?
Maybe it is interesting. Maybe interesting. We don't try before.
We haven't tried this yet. Yes.
Okay, because as for me, it will be really interesting in such interesting process. So, colleagues, do you have any questions? Maybe Professor Pesin?
No, I think that maybe we can give 5 minutes coffee break for people, for others. Okay.
We have one question in chat from Professor Liz. Did anyone model residual stress in HTP disks? Residual stresses in HPT disks?
Yes, I think. But residual stress we see in amorphous materials, bulk amorphous materials, metallic glasses after high pressure torsion. Because distribution of microhaders show us what some остаточной деформации. Residual stress. We can see.
Can I answer the question? I'm Tim. I already measured residual stress after hypertorsion. I measured the residual stress using neutron scattering. So it was already published some years ago. Probably I can support it. So it was measurable, and I did using simulation and the measurement. Thank you.
Thank you.
So, any questions? Okay. Sorry for this trouble with schedule. We have about 4 minutes for short coffee break. And we will begin from the report of Pietro Rebisan from National Institute for Nuclear Physics, Padova Division, Italy, in 3 minutes. Thank you. So colleagues, we should continue. Professor Rebesan, are you here?
Hi, Dimitri. I'm Claudio from Padua.
Hello.
Unfortunately, Pietro Rebesan wasn't able to do the presentation, so I will do it on his behalf, if it's okay with you.
Okay, you're welcome. You can
Okay,
start.
thank you very much. I will start the presentation. Let me tell me if you can see the, just a second. Can you see the presentation?
Yes.
Okay, perfect. So I would like to talk about the interface analysis of additively manufactured pure molybdenum on IZ304 stainless steel building plate. First of all, I would like to talk about, just a second, because, okay, yes, a quick introduction about the selective laser melting process, but I know that everybody here knows what I'm talking about. So the additive manufacturing process is a process that joins two materials to make object from 3D model layer by layer. And in this process, raw material is metal powder and the energy input is a laser beam. There is a little video here that should start. Yes, perfect. So we use an EOS M100 machine, and the specification of the machine are summarized in this table. The process was performed under controlled atmosphere of argon gas, and this process have many benefits, but also has a lot of limits. One of the biggest limit is the amount of processable materials. The only processable materials that can be used for 3D printing is materials that are weldable, and therefore, the general purpose is to study materials that are not well studied yet for this process. And the choice of this material is related to the experiment of the National Institute for Nuclear Physics. For instance, in the picture, I'm not very expert in the experiment that they are doing at the National Physics Laboratory, but I will try to talk about it a little bit. The picture shows the first Phibiad ion source, which is the core of the selective production of exotic species project for the production of extremely pure radioactive ion beams located at the National Laboratories of Legnaro. Because of the tight tolerances and the design and assembly to respect and the high temperature reached by the part during the exercise, it has been thought that the refractory metals additive manufacturing process could be a good research opportunity. Refractory metals belong to the group of transition metal and are also called ultra high temperature materials. They exhibit a very high melting point, very high density, thermal conductivity. Sorry? Oh, very high thermal conductivity and high hardness. To make them suitable for many applications, for instance, tungsten is a promising candidate for plasma-facing materials in future nuclear fusion devices. In biomedical field, the proliferation of human osteoblast on tantalum is excellent in comparison to the more commonly used titanium grade 5. And also for space and aerospace application, for example, in order to increase the high temperature capability of aerospace gas turbines or for the rocket nozzles of the future generation. So the purpose of the study is to optimize the process parameter in order to produce refractory metals component by selective laser melting on the machine that I talked about before. And we start with the characterization, the material characterization and the process parameters tuning. We produced blocks in order to perform microstructural characterization and density measurement, and other samples to test the mechanical properties, the thermal conductivity, and the emissivity at room and high temperature. The production of the from the very beginning, there was some issue because we tried to print pure molybdenum on IZ300 and 4 austenitic stainless steel, and there was not very good adhesion, which compromised the whole printing. So the main purpose of the study is to perform the interface analysis of the additive manufactured molybdenum on the IZ304 stainless steel in order to understand what was going on specific at the interface. So first of all, we performed some thermocalc simulation in order to understand what could form in the case of a high molybdenum content and the IZ304 under equilibrium condition, because thermocalc is only able to perform equilibrium simulation. And it can be seen that with equal proportion of molybdenum and austenitic stainless steel, due to the high chromium concentration of the stainless steel, there are a lot of secondary phases forming. That could form. The most important and deleterious one is the sigma phase, which is also found in the 304 stainless steel when heating at higher temperature for a longer period of time, and in duplex stainless steel for a lower amount of time, but at the same temperature. Other secondary phases could precipitate, but due to the very fast cooling rate of the additive manufacturing process, it is very unlikely to have been formed. So rapid solidification and cooling induced by laser powder bed fusion is obviously not represented by equilibrium condition, and segregation during solidification is would not say neglected, but is hindered and limited. So it can be assumed that because of the that under a given temperature threshold there are limited diffusion. And so the large variety of intermetallic phases expected at the intermediate dilution values would most probably be reduced to a limited number of constituents under real condition. So we started with the production of a disc of 40 millimeter of diameter and 0.5 millimeter thickness. The production of the disc, of the molybdenum disc, failed because of the interface issues between molybdenum and austenitic stainless steel. So we sliced the disc with electric discharge machine in order to reach the interface between molybdenum and the austenitic stainless steel. We then performed a metallographic preparation of the surface exactly at the interface between the two materials. By means of EDS elemental mapping, we can see that molybdenum, there are, first of all, there are plenty of molybdenum particles that are unfused, unmelted, and are those very bright spot in the, this is the molybdenum printed region, and this is the IZ304 backplate. The molybdenum is absent in the outside of the printed region, while meanwhile iron, chromium, and nickel can be seen diffused into the 3D printed region. We performed a line analysis across the surface on the top, always on the top view of the material, and we can see that there are some undissolved molybdenum particles in the matrix surrounded by a higher molybdenum content iron chromium matrix. These peaks that nearly reaches 100% are in correspondence of the unmelted molybdenum particles. There are different gray level of the solid solution, which correspond to different molybdenum content solid solution. On the far right of the line analysis, the composition measured was that of the austenitic 304 stainless steel. The molybdenum peaks, as I said before, are in correspondence of the molybdenum unmelted particle. While on the right image of the slide, from the unmelted molybdenum particles, there are some micro cracks that start from the particles and protrude into the matrix where the molybdenum content is higher. We performed the XRD analysis on the top surface of the sample, and there are a lot of reflections. The first one and the narrow peaks corresponds to the unmelted molybdenum particle, which is this one in the green circles. And it has to be noted the absence of the peaks of the austenitic phase due to the formation of a body-centered cubic solid solution consisting of molybdenum, iron, chromium, and nickel. The lower intensity and the broadened peaks on this one with the blue triangles refers to this solid solution of molybdenum and iron. The broadening of the peaks are, yes, due to microstrain, but because of the fact that there are different amounts of molybdenum dilution in the solid solution, this solid solution doesn't have a unique lattice constant, but it depends, of course, on the molybdenum quantity, which result in an overlap of reflections at different 2 theta angles. And the apparent asymmetry, I'm talking about these peak tails of the iron molybdenum solid solution, is due to the overlapping of the sigma phase reflections. And no other phases have been found despite a thermochemical simulation like mu phase, Laves phase, G phase, and so on. We perform also EDS elemental mapping on the cross section of the sample, and we can see that, and as well line analysis, which will be presented in the next slide. So we can see that iron diffused into molybdenum 3D printed layers. This is referring to the iron, and this is the 3D printed molybdenum phase. And we can see that there is an interdiffusion of iron into the molybdenum. Together with chromium and nickel, while molybdenum is mainly restricted to the 3D printed zone. The big crack that can be seen here horizontally is in correspondence of the where molybdenum exceed 48% in concentration into the solid solution. And there are also cracks which are parallel to the cross-section direction. And they are following the higher content molybdenum, iron molybdenum solid solution. The line analysis, molybdenum content can be seen that decrease linearly from this end to the toward the 304 building plate. As I said before, the big cracks is in correspondence of the for approximately 40 to 45% weight molybdenum in solid solution, and also there can be seen different morphologies moving from the molybdenum 304 interface, this zone, to this zone, which are shown in these 2 micrographs. So here are some more or less equiaxed molybdenum grains, while close to the interface there are a lot of dendritic structures and partially melted and unmelted molybdenum particles. So, as I said before, dendrites of molybdenum and 304 steel solid solution phase with higher molybdenum content are surrounded by lower molybdenum interdendritic region, in which can be seen some shrinkage cavities, which are these black spots. And they are much more evident in this slide, which lead to failure of the component. Also, it has not to be confused the different gray levels with different molybdenum amount. These gray levels are due to electron channeling contrast, which is a sort of orientation mismatch between the electron beam of the scanning electron microscope and the crystal structure of the materials. And moving forward, we tried to dissolve, to extract the precipitates, the secondary phase precipitates that formed into the material with hydrogen peroxide. Unfortunately, it was leached only higher content molybdenum region, leaving behind, I would say, quite interesting iron molybdenum sponge. Here are evident these round region of unmelted molybdenum particles, and they are surrounded by a lower molybdenum content interdendritic matrix. Some cracks can be observed emanating from the spot where the unmelted particle were present. The overall molybdenum content in the sponge matrix did not exceed 48% because of the higher content molybdenum body center cubic phase was leached by the hydrogen peroxide. We were able to do a successful extraction of secondary phases particle using boiling aquaregia. And as a reference, sigma phase extraction from duplex stainless steel can be seen on the left-hand side of the slide, and it is used as a reference for the sigma phase extracted from the iron molybdenum dissolution. And morphology and composition of the secondary phases extracted from iron molybdenum solid solution is very close to that of duplex stainless steel. We also performed XRD analysis on the precipitate, which are not displayed here because they are still ongoing. I was not able to perform a deeper investigation, but with the preliminary analysis, I can say that the XRD confirmed the presence of a sigma phase and the absence of any other secondary phase. So in conclusion, despite the thermochemical simulation predicted a plethora of secondary phases, only sigma phase was observed due to the out of equilibrium additive manufacturing process. And of course, the very fast cooling rate hinders the diffusion. XRD on the top surface of the interface confirmed the presence of sigma phase and a BCC solid solution of molybdenum in different amount and iron, chromium, and nickel. Dilution of austenitic stainless steel and molybdenum was observed thanks to the elemental mapping and EDS analysis, and we were able to see that the big cracks which led to failure in the additive manufacturing component is approximately reached when when molybdenum content is 45%. We were also able to do a successful extraction of secondary phases particle using boiling aquaregia, and the XRD analysis confirmed that the secondary phases extracted are sigma phase. So I would like to thank you for your kind attention, and if you have any question, I will be pleased to answer them.
Thank you for your report, and thank you for your colleague. Colleagues, do you have any questions? I have one question. This is some kind of discussion.
Yes.
If we take into account all these features with crack initialization, crack propagation, all these thermal distributions, and so on and so forth, what about performance of such methods or production methods in the future, or in perspective? If we speak about, for example, massive production, not tons, but maybe kilograms.
Yes. That will be very interesting. I'm just here reporting that this is a very specific and very narrow field in which additive manufacturing could be successful. In the yes, those are very, very particular samples that you are trying to make and using very exotic materials for a very strange and cutting edge ion beam source, which the cost of the 3D printing is taken into account. Regarding the mass production, that is complete another story. And I'm not an expert on additive manufacturing. I just performed the metallurgical analysis of the interface. So unfortunately, Pietro was not able to be here to answer the question regarding the additive manufacturing process, but I can provide you the answer in a second time if you want.
Okay. And one more question, from material science point of view.
Yes.
Maybe not material science, who knows. What about residual stresses in during some production? We have melting and so on and so forth.
Yes, yes. So there are some big issues with this material, not just at the interfaces. This is one very big issue where the materials, where the sample did not adhere to the building plate, as I said before, but also because of the very high melting point, there are a lot of thermal cracks in the material. Disregarding the issue of the building plate, we solved the problem with the building plate with copper. But the problem, the issues with the thermal cracks are still there. And because of the high melting temperature and the higher ductile to brittle transition temperature of this refractory material, which is around 400 degrees centigrade. So there are a lot of troubles. We are trying to measure the residual stresses on molybdenum. We didn't have any data yet, but it's scheduled to do that measurement, and of course that will be very interesting to investigate. But we are going to do it.
Okay, thank you.
You're welcome.
Do you have any question? No, thank you. Thank you for your report. We should go to the next report from Belarusian State Technological University. Dmitry Kuis. I saw BGTU in chat. Are you here? We don't hear you. One moment, I will try to ask them to switch on the microphone.
Dmitry, are you here?
Unfortunately, it seems no.
Okay, maybe we have a real coffee break.
Okay. See you in 20 minutes. So colleagues, we should continue. Next report should be from our colleague from Brazil, Roberto Figueiredo. As I remember, I have yes, I have a pre-recorded presentation from him, but I see him in chat.
Hello, Dimitri. I'm here.
Hello. Yes. What do you prefer, to make report personally, or I can start your report?
I think it's better to show the pre-recorded presentation, okay, and then I can answer any questions. So make sure that the timing would be good.
Okay, no problem. Do you see it, colleagues?
Yes.
Hi, everyone. My name is Roberto Figueiredo. Before I start the presentation, I would like to acknowledge the organizers for putting on this conference in memory of Professor ZHILYAEV. Professor ZHILYAEV was a great and passionate researcher, and I will always remember him from discussions on conferences and coffee breaks. But Alex was also a very nice person to talk to outside of professional buildings. The title of my talk is on magnesium matrix hybrids produced by high pressure torsion. This is an ongoing research funded by Serra Pilheira Institute. Moara Castro is a PhD candidate who carried out most of the hard work, and we had many collaborators in this. It is well known that severe plastic deformation by high pressure torsion can consolidate metallic particles. Early papers by Bridgman report consolidation of boulders, and early papers, especially from researchers in UFA, report the fabrication of metal matrix composites using HPT. And I selected these two papers just to remind us that Professor ZHILYAEV also carried out research in this area and played a significant role in this area as well. So it is well known also that high pressure torsion processing can refine the grain structure of metallic materials. And magnesium is no exception for this. And we can see here that pure magnesium processed by HPT has ultrafine grains. And I would like to call the attention to some facts that are not so well known and motivated us to use magnesium as a matrix for production of hybrids. For example, we know that coarse grain pure magnesium can be considered a brittle material. However, refining the grain structure in this material below a few microns can improve ductility. And this picture here shows the appearance of tensile specimens of pure magnesium processed by HPT. And we can see elongations of up to 300% in tension at room temperature in this material, which confirms the exceptional ductility that we can introduce in this material. Also, severe plastic deformation seems to change the corrosion behavior in magnesium. This graph here shows the response of pure magnesium with different processing history to an electrochemical impedance spectroscopy test. A rough approximation, a rough simplification of this test, we can say that the larger the arc, and the response of the material here, the higher the corrosion resistance. And we can see that severe plastic deformation by ECAP and by HBT improves the corrosion resistance in this material. And this is of major importance for biological applications because magnesium can be used as temporary implant and controlling and reducing the corrosion rate in this material is of major importance in this field. So what about magnesium matrix hybrids? How do we process them? Basically, we start with magnesium particles or magnesium machine chips. We mix it with different materials. We press to produce green compact and then process this green compact by HBT to consolidate it. We actually studied several systems in this area, and these systems we divided basically in 3 different objectives. One is to understand the mixing between magnesium with other metallic materials and its consequence to mechanical properties. The other aim is to introduce hard ceramic particles to increase the strength of magnesium to produce a very high strength hybrid. And the other aim is to produce a biodegradable magnesium matrix hybrid with the incorporation of bioactive material. So I selected 3 systems to bring to this presentation today. The first one is the magnesium zinc system. And it's a very interesting system because magnesium and zinc can be ductile if the grain size is small enough. So we produce hybrids with different proportions of magnesium and zinc, and we process HBT with different number of turns and compare it to pure magnesium and pure zinc. And these SEM images here shows the appearance of the surface of the sample, and the bottom left in each image is the area near the center where the strain imposed by HBT is smaller, and the top right is the area near the edge of the disc where the amount of strain imposed is higher. And we can see that at low levels of applied strain, we can tell apart magnesium and zinc phases, but as the amount of strain imposed in the material increases, we cannot tell apart these phases, and we have significant mixing between them. So we actually used a modern transmission electron microscope to capture high angular dark field images, and using this technique, like the contrast in the images is associated with the atomic weight of the elements. And the bright areas here, they're associated with zinc, and the dark areas are associated with magnesium. And this image here working from a magnesium 20% zinc hybrid processed by 20 turns of HBT. And this image here shows a particle, a phase, a zinc phase with significant fragmentation of it. We can see fragments of zinc just being removed, detached from the zinc phase. And we observe that this fragmentation plays a significant role on mixing between the phases. We actually observe particles of zinc as small of 2 nanometers in size. And such small particles can only be attributed to fragmentation of the original zinc phase because precipitation of zinc is not expected in this system. We expect precipitation of magnesium zinc intermetallic, which we actually also observed. And we use micro-hardness test to track the mechanical behavior, mechanical strength evolution as a function of the strain imposed in HBT. And we can see that pure magnesium and pure zinc, they do not display significant hardening as reported in literature by many researchers in these pure metals. However, the hybrids, all the hybrids, they display higher strength even at low levels of strain imposed in HBT. And this improving strength is associated to the presence of interface boundaries and some solid state solution that takes place in this material. But interesting point is that these hybrids, they also display a second stage of hardening as the amount of strain imposed to the hybrid increases. And this second stage of hardening leads to a very high level of hardness, and this is associated, is attributed to the fragmentation of the phases, the formation of segregations of alloying elements along grain boundaries, and precipitation of intermetallics. So we can control the strength in these hybrids by controlling the composition and the amount of strain imposed to them. Another system that is very interesting is the AZ91 alumina system. The AZ91 is a widely used commercial magnesium alloy with high strength, and we actually added hard ceramical particles in order to produce a very high strength hybrid. So we processed pure AZ91, we consolidated pure particles of AZ91 using 20 turns of HPT and using 50 turns of HPT. And we noticed that with increasing the number of turns, we actually further refine the grain size. We produce samples with grain size as small as 100 nanometers in size. But with the incorporation of alumina particles, we observed that a further grain refinement takes place. So these hard particles contribute to grain refinement. So we produced a sample with an average grain size in the range of 80 nanometers, and we expect this to be the higher strength of this sample, not only because it has alumina particles, but because the grain size is small. But we observed the opposite trend. The hybrid, which has the finest grain structure and incorporation of the hard particles, displayed lower hardness of this of all the samples. And we attribute this to a limit in grain refinement hardening in this material. So it seems that if we go below a certain level of grain refinement, we start to see softening in this material. And this is easier to observe if we compare our data to data for the AZ91 alloy in the literature. And we can see that for coarse-grained AZ91 material, this material follows a conventional Hall patch behavior in which decreasing the grain size is associated with increasing the strength. However, many researchers have shown that if the grain size in pure magnesium or magnesium alloys is refined below a few microns, we can see a change in slope in the Hall patch relationship. And this change in slope is attributed to a decrease in twinning activity in fine-grained magnesium. And our data confirms that there is this change in slope, in Hall patch slope, but also our data shows that there is inverse Hall patch behavior if the grain size is smaller than 100 nanometers. And this inverse Hall patch behavior is attributed to creep mechanisms such as grain boundary sliding, cobble creep, which the theoretical predictions are also plotted here, and we can see that our data agrees with the theoretical prediction. So the last system that I would like to show you is the magnesium hydroxyapatite system. Hydroxyapatite is a calcium phosphate material with composition similar to the human bone. So many research groups have worked on developing these hybrids with magnesium with hydroxyapatite, and they usually use hot extrusion or melting to produce the hybrids. And our aim is to use high pressure torsion, not only to avoid the high temperature step in processing, but also to refine the grain structure of the matrix. So basically, we mix pure magnesium with hydroxyapatite and use high pressure torsion to consolidate it to produce a continuous magnesium matrix, no sign of cracking in this hybrid with well dispersed second phase particles. We use EDS mapping just to confirm that there is no solid state reaction between magnesium with hydroxyapatite. You can see here calcium, phosphorus, and oxygen in the second phase particles. We also tested the mechanical integrity of this hybrid by carrying out tensile tests, and we can see that the strength of the hybrid is actually higher than the strength in pure magnesium, and it displays fairly good elongation, fairly good ductility, And although the elongation is not as high as 10% or 100%, we have to recall that this hybrid contains several hard and brittle particles of hydroxyapatite, which can nucleate cracks. So any elongation here is welcome. We also carried out a preliminary biocompatibility test in which cells are placed in contact with the hybrid, and their activity is measured and compared to the activity of cells that were not placed in contact with any material, and the response is pretty much similar, so it shows that there is no problem with biocompatibility, at least in this preliminary test. But any research in this area has to evaluate the corrosion behavior of this material. And we carried out electrochemical impedance test. And if we remember from the beginning of this presentation, the larger the arc in the response of the material here, the better the corrosion resistance. And the magnesium hydroxyapatite hybrid actually display small arc here. You can see that the scale bar here is 10 times smaller than the scale bar here for pure magnesium, which we use for comparison. And this result was actually expected because if we place two materials in close proximity, we can induce the formation of galvanic couple, which can accelerate corrosion. However, our experiment shows a very interesting effect. Depending on the immersion period of time of the hybrid, the response in this test has a very high corrosion resistance, actually higher than the observed in pure magnesium. So it seems that as corrosion takes place, this material is developing a corrosion product layer that protects it from further corrosion. So we went on to evaluate this corrosion surface layer, the corrosion product layer. We used photosyl beam to dig a hole on material, and here we can see the corrosion product layer on the surface and the substrate, the material below here. And we don't see magnesium in the corrosion product layer, and we see a lot of phosphorus and calcium, which suggests that there is formation of a very good corrosion product layer that protects this material and has potentially good biological response. So in summary, it is possible to produce a magnesium matrix hybrids using HPT. Investigation in magnesium zinc system revealed that fragmentation plays a major role on mixing these phases. Investigation in the AZ91 alumina hybrid revealed there is a limit in grain refinement strengthening in magnesium alloys. And investigation in the magnesium hydroxyapatite system revealed that it's possible to produce sound, strong, biocompatible, bioactive, biodegradable magnesium 8 matrix hybrids with good corrosion response. So with this, I would like to thank you all for your attention.
Thank you.
Thank you for your presentation. Colleagues, do you have any question? We have our personal specialist in magnesium.
No. Okay, thank you for a great presentation. I just want to clarify something. Did you provide corrosion resistance for AZ91? Or probably the last part of your presentation was about all magnesium hydroxide alloys. I didn't catch it.
Excuse me, I don't know if I understand your question. Did you ask if I used AZ91?
Did you provide corrosion resistance measurements for AZ91 alloys?
Okay. I didn't show in this presentation, but we published a paper where we compared the corrosion resistance of 3 commercial alloys, the AZ31, AZ91, and the ZK60, and pure magnesium, both before and after HPT processing. And it seems that HPT does not compromise corrosion resistance of these materials, and in fact, some of these alloys display better corrosion resistance after HPT.
Okay, and another one general question. Whether you ever notice some influence of the initial magnesium alloy texture on behavior during HPT? Because I have never seen such work. Maybe I didn't look carefully, but maybe you noticed something.
Okay, so we didn't check the texture effects on this, on the corrosion behavior of this pure magnesium or magnesium alloy. But the samples that we use for testing is the samples processed by HPT, and we only had samples that are very small, 10 millimeters diameter and very thin. And so it's difficult to evaluate the corrosion on the sides. We can only evaluate corrosion on one surface. And that surface is expected to have a basal, the basal planes parallel to it's a texture, characteristic texture from HPT. We are now trying received samples from HPT, which are thicker samples, larger samples. So now I want to compare the corrosion on different sites to see if the texture will play a significant role on it.
Okay, thank you for your presentation again and for your answers.
Thank you, Daria.
So thank you for your presentation, because due to time zone difference, you have early morning now. Yes.
Yes.
Okay. Thank you. Thank you. It was difficult for you, but thank you.
Hello. I'm sorry. That is Magnitogorsk. Тут немножко сбилось у нас, потому что по программе мы должны были быть позже и прошли тут немножко у нас учебный процесс, поэтому отвлекались. Как нам здесь поступить сейчас?
Так. Смотрите, а вы мобильный по времени сейчас? Мы
в принципе, да.
Да, но только вот тогда получается на 16-ю позицию там доклада не будет.
А это на какое время у нас получается?
Так, это по Москве 14:40. Удобно? Не все увидели обновленную.
По Москве и у нас 14:40.
Ну да, у нас просто в Магнитогорске.
Ну, а сейчас нельзя уже будет сделать, да? То есть мы смещаем тоже было.
Просто тогда все сместятся. Александр Моисеевич, что скажете?
Ну, нужно все-таки в 4:40 и лучше.
Ну, в 14.
14:40, да.
2:40, да?
2:40, да.
Да, хорошо тогда, спасибо.
Вам спасибо.
Вам спасибо.
Unfortunately, we have a few troubles due to new program, because we try to combine a lot of time zones and a lot of speakers. So unfortunately, something goes wrong. Next report is from Colorado School of Mines, USA. Terry Love. I see you in chat. Are you here? I think no.
Terry Lowe, are you here?
So maybe that's why we can work with our colleagues from Belarus. Are you here?
Okay. Okay.
Все.
Только у нас нету видео, тут небольшие проблемы.
We had troubles with video.
Пожалуйста.
Could you start?
Yes, of course.
Hello, dear colleagues. Unfortunately, my English is not very good, so the report will be made by a specialist of our department, Anastasia Kutas.
So may I start our presentation? Can you hear us?
Yes, yes, everything is okay. You can start.
I would like to present to your attention our report on synthesis of aluminium, titanium, ferrum, chromium, nickel, and nitrogen protective coatings by the method of vacuum arc deposition from a separated vacuum flow. The high entropy of multi-component alloys lead to special structural states, in particular to structures with uniformly distributed nanoscale inclusions or to amorphous structures, and thus to unique functional property. This is high hardness even after annealing at temperatures above 1000 degrees Celsius, high thermal stability, hydrophobicity, superelasticity, increased resistance to wear, corrosion, and oxidation, high rigidity, strength, and toughness, etc. The stability of the structure and composition, as well as the high operational characteristics of high entropy alloys, create great prospect for the possibility of forming coatings on their basis. This makes it possible to improve the surface characteristics or use them as protective films that prevent the ingress of harmful impurities into the near surface layers of the product. The use of nitrate coatings based on high entropy alloys is a promising direction in various fields of technology and biomedicine. In this work, aluminium, titanium, ferrum, chromium, nickel, nitrogen were selected for research, which should provide the possibility of forming a wide range of various phases and complex compounds on their basis, as well as the sufficient content of the plastic metal phase for relaxation of internal stresses. So let's move on to experimental method. In our work, we used the technology of a vacuum arc deposition with the plasma optical separation system on a modified installation with two cathode evaporation. You can see it in the figure. So the cathode materials were titanium and aluminium. The inserts were made of steel containing 0.08% of carbon, 18% of chromium.
Как вы себя чувствуете? Добрый день.
Да, хорошо.
10% nickel, 1% of titanium. So let's have a look at the figure number 2. The arc current and the cathodes varied from 60 to 90 amperes. Silicon, hot alloys, and steel containing 0.4% of carbon and 1% of chromium were used as a base for the deposition of coatings. The deposition of coatings was carried out when the potential from -80 to -90 volts was applied to the base, and the constant nitrogen pressure is 0.4 Pascal. The initial pressure in the working chamber is 3 multiplied by 10 to the minus 30 degree Pascal. Now let's move on to experiment result. The surface morphology and structure of the coatings are characterized by uniformity and the lack of a columnar structure specific to mononitrate coatings applied by this method. You can see it in the figure number 4. In this case, a clear interface is observed between the coating and the titanium layer, sublayer. According to the result of X-ray diffraction analysis, the coatings, aluminium, titanium, ferrum, chromium, nickel, nitrogen, deposited by the vacuum arc method using a separation system, were a solid solution based on titanium, aluminium, nitrogen, with the latest parameter of 0.42 microns. Let's have a look at figure number 5. The analysis shows that the formed coatings are not textured. A noticeable broadening of reflections indicate the formation of a nanoscale structure of the coatings. According to calculations, the grain size is from 8 to 40 nanometers. Experiments have shown that the use of a plasma optical separation system significantly affected the mass transfer of elements into the coating. It was found that the content of both iron and nickel in the coating significantly decreases in comparison with their content in the cathode. Moreover, a similar effect is not observed for chromium. The change in the arc current at the cathode mainly affects the content of titanium and aluminium in the coating. With the rise in the arc current of the titanium cathode, the titanium content increases. The effect of the displacement potential based on the elemental composition of the coating has its own characteristics. When the potential changes from minus 80 volt to minus 90 volt, the greatest changes occur with the concentration of elements such as titanium and aluminium. The ratio between the content of titanium and aluminium decreases. You can see it in the figure number 6. The phase composition of the coating also changes. It can be seen in the figure number 5. According to the obtained result, the titanium nitrogen and titanium 3 aluminium 2 nitrogen 2 phases are recorded in the composition. Studies of the electrochemical behavior on the base coating system have shown that the elemental composition of the coating significantly affects its corrosion resistance. A comparative analysis of the obtained result shows that the main influence on the increase in the density of the ion current of anode, the solution, and the polarization resistance is exerted by the concentration of aluminium and the coating composition. You can see it in the figure number 7. So when the concentration of aluminium in the coating composition changes from 10 to 31 atomic percent, the stationary electrode potential of the coating system is refined from minus 0.005 volt to 0.11 volt. The current density of the anode solution is reduced. As shown by the comparative result of elemental analysis and electrochemical studies of samples, look at the table on the slide 4. A change in the displacement potential during the formation of coatings causes a shift in the stationary electrode potential of the coating-based system to the negative area, which is due to an increase in the amount of iron in the coating. However, there is significant decrease in the current density of anode dissolution and an increase in the polarization resistance of the samples, which indicate the ability of the coating to spontaneous passivation, which ensures a high resistance of the coating-based system to general corrosion. Figure 8 shows the result of friction test. It can be seen from the figure that the increase in the aluminum content in the coating reduces the coefficient of friction of the coating. That is, improves anti-friction properties. For product operating at high temperatures, it is necessary to ensure their high micro-hardness and resistance to oxidation at high temperatures. The study of the heat resistance of samples made of hot alloy with coatings aluminium, titanium, ferrum, chromium, nickel, nitrogen showed that the coatings provide high micro-hardness of hot alloy samples up to 29 hectopascal, up to 1000 degrees Celsius. You can see it in figures number 9. The high micro-hardness of coated samples may be due to the retention of their nanoscale structure. Grain size doesn't exceed 35 to 40 nanometers, as well as their resistance to oxidation at high temperatures. At the figure number 10. The high resistance to oxidation of a hot alloy with coating aluminium, titanium, ferrum, chromium, nickel, nitrogen can be due to both the high heat resistance of the elements included in the coating and the formation of a dense oxide film on its surface, which impedes the diffusion of oxygen deep into the coating material and prevent further oxidation of the coated alloys. Well, to sum up, we can say that the possibilities of forming multi-component coatings by the method of vacuum arc deposition using plasma for separation have been studied. The selected technology makes it possible to form coatings with a dense, homogeneous structure, uniform distribution of elements over the coating volume. The high corrosion resistance of the coatings is due to the synergistic effect of the nanoscale structure and the ability to form surface oxide layers in corrosive environment. So I think you have covered all points on synthesis of our protective coatings by the methods of vacuum arc deposition from the separated vacuum flow. Thank you for your attention.
Thank you for your report. We have a few minutes for questions, colleagues.
Okay.
Alexey Georgievich, we don't hear.
Yes, can I ask a small question? Dmitry and Anastasia, thank you very much for a very interesting presentation. Could you show the slide number 5?
Of course.
Okay. How have you measured the value of friction coefficient?
Схема палет-диск использовалась. Ну, на фрикционных машинах.
Can you translate Dmitry's answers for international?
It was measured on friction installation machines.
На трибометре.
I understand Russian, but my colleagues cannot understand. Okay, thank you.
Friction machine. It was measured on friction machine.
Thank you.
So thank you for your report. And now we have again small changes in schedule. We have guests from the USA. We have a serious time zone difference between Russia and the USA, and that's why I want to invite Professor Love to share his screen. You're welcome.
Okay, good afternoon. It's a pleasure to be with everyone, and also to honor Dr. ZHILYAEV. He was an inspiration to me, to everyone. His just his jovial spirit, his very encouragement was a gift, and I'm sad that he is gone from us now. Let me see if I can share my screen. So give me a moment here. I think I will do the same as the previous speaker and leave the slides in not presentation mode. Let's see if I can do this. Let's see, let's close this and get to the top of this. Perfect. Okay. So one moment. There we go. All right, this is a very simple piece of work. Let's see if we can enlarge that. And again, if there's any technical difficulties during the presentation, please let me know in the chat. And again, today we will talk about high-speed continuous equal channel angular pressing of 316L vacuum melted stainless steel. And you pick this material because it has commercial significance for the medical metals industry, but also because it's particularly, we expect it to be particularly difficult to work with. Now, this is work by myself, a collection of my students, and then colleagues at Fort Wayne Metals who have recently started production of titanium and other alloys by continuous equal channel angular pressing. Okay, and again, I just want to share that this is dedicated to Alexander ZHILYAEV, Truly a great man. Okay, so an outline for our presentation today is to provide a little bit of background on ultrafine grain metal production, then talk about the materials and methods, results, and summary. So very, very straightforward. Now, you know, I call this high speed continuous equal channel angular pressing, in part because all the work is conducted at rates that are much higher than conventional ECAP. So let's take a look at why that matters first. So a little bit of background on economics and the importance of speed in metal processing. And we look at that by looking at some of the conventional metal forming processes, you know, rolling, extrusion, drawing, swaging, and the rates at which those are performed traditionally. And of course, there are a wide range of rates for different alloys and different parts of the metal production industry. But I picked some examples where there were citable numbers from the literature. So, for example, in performing bar extrusion of titanium, not 316 stainless steel, but of titanium, that generally you're at speeds that are below 10 millimeters per second. And there's a reference by Fiorentino showing the range of rates that they had used. Bar swaging, again, fairly slow, 6 to 20 millimeters per second. And of course, having done a lot of this myself on, in the lab and a little bit on the plant floor, and again, mainly for titanium, the rates at which automatic feeders that introduce bars into swagers are fairly slow as well, so up to about 20 millimeters per second. Tube extrusion of 316 stainless steel. There's Hansen shows examples of where, and this is in Scandinavia, where you're doing extrusions at rates up to about a half meter per second. But in this case, at very high temperatures, between 1100 and 1300 degrees C. And then, of course, we make a big jump. If we look at wire drawing or wire rolling or rod rolling, those rates can be quite high, up to many meters per second, 75 to 135 meters per second. Now, in contrast, for ECAP, we find fairly low rates published in the literature. So I've shown two examples here, Sun et al., Persic et al., where they have rates that are on the order of 1 millimeter per second or less, 0.05 millimeters per second. And of course, the first example there was Sun is 120 degree die. Persic uses a 90 degree die. But now the next two examples of actually a 316L, there's 0.1 millimeters per second. And then Rapici and Karaman were up at 12.7 millimeters per second. But that was up at 700 to 800 degrees C. Okay, so generally for the lower temperatures, which we like to use when you're making ultrafine grain materials, the rates are quite low. Okay, so let's look at what would go into choosing a rate for 316 stainless steel for continuous processing to higher rates. So of course, one of the concerns is adiabatic heating. And of course, 316 stainless steel has a notoriously low thermal conductivity. So here are a couple examples below us, one from Karami and another from Vasquez Fernandez. This is for aluminum, which is subjected to ECAP at 90 degrees here, or in a 90 degree die, but at room temperature, at least it starts at room temperature, and then they measure the temperature after ECAP at a half a millimeter up to 2 millimeters per second. And they see anywhere from, well, let's see, it starts at 20, so a 20 to over 100 degrees C temperature rise. And of course, now these are simulations that they've done. In addition, if you look here at, and this actually is at 316 stainless, not L, but 316 stainless, where they take a tensile sample and pull it at a variety of strain rates. And those rates, even when they're quite small, result in some delta T, some change or increase in temperature in this configuration. And of course, this is really quite small. It's only 2 millimeters width for this specimen and about 8 millimeters long. But nevertheless, at least when they're up at 85, which is higher strain rate than occurs in any of the work I'm going to show you in a moment, the temperature increases on the order of 40 degrees after a strain of 0.3. Okay, so that, of course, encourages destabilization in the formation of adiabatic shear bands and microscopic shear bands as well. Now, another factor to consider, of course, is the temperature dependence of the flow stress of stainless steel. And of course, one of the factors that shows up here is that as you're at lower temperatures, and this is literature from Dion, as the temperature becomes lower and lower, and the data shown here on the left are for 316L in the annealed state. Here you have a mixture of 316 and 304 stainless steel. But in any case, as you go into lower temperatures, the rate at which your temperature sensitivity actually increases. But in any case, that is the amount of change in strength increases as you change the temperature a bit more. So what this tends to encourage you to do is to pick a higher temperature where a difference in strain rate is not going to cause as much trouble. Now, another consideration is that the heat capacity is also temperature dependent. And so if you look at room temperature, the heat capacity of 316 stainless steel is around 468 joules per kilogram degree K. And of course, now this plot here is actually for two different steels. The SAF 205 is closer to 316, but neither of them are 316. Just for comparison, the heat capacity of water is, of course, up there at 4,000. But in any case, as you have a higher heat capacity, you have a better ability to absorb and manage heat in the billets. Okay, but one more consideration is, and that is the so-called plastic instability stress, or if you look at Considere's criterion, where d sigma d epsilon is equal to the stress. And of course, in a tensile test, that's the point at which you start to get tensile instabilities. So that also depends upon temperature. And in fact, it increases with decreasing temperature. So that tends to cause us to want to choose a lower temperature. Okay, so you take all of these factors in combination and say we need to pick a temperature that's reasonable. Now, what I'll tell you right now is that we ended up choosing a temperature for 316 stainless, which is an 18% chromium, 9 or so percent nickel stainless steel. And we ended up choosing 300. But let's look at the actual material here a little bit more. So we used stainless steel 316L VM from Fort Wayne Metals. Starting stock was 1 meter bar, 12 millimeters in diameter. And the table that's shown here are the properties that Fort Wayne Metals publishes for their conventional rod. So no ECAP here, just conventional, not ultrafine grain. And so so for annealed properties, they have a yield strength of 310, the ultimate tensile strength of 627, but a very good elongation to failure to 42%. Now, as they add cold work, which you can get from them to this bar, just conventional cold work, whether that be by swaging or rolling, you can see the elongation to failure plummets, going down to 8% after 20%, and then 2.5%. Generally, in the medical device industry, you're wanting to have elongations to failure above 10%. So it's a little bit difficult to consider using these higher strengths, so you can get ultimate tensile strengths up above 1100, but that's not really a very usable material for many applications. Okay, so let's look at what we did here. So first, we conducted continuous equal channel length pressing, and I'll show you a little bit of that over a range of temperatures, again, using starting with 1 meter long bars. And then doing that between temperatures of 100 and 450 degrees C's to explore what we can find in that range. And then at feed rates between 1 millimeter per second, comparable to conventional ECAP, and 42.5 millimeters per second. Then we did characterization, classic EBSD, and then a bit of mechanical testing. Okay, so let me move ahead here. So the continuous ECAP looks something like this. And again, you have a rotating wheel with a channel in it. And what happens is, of course, in the first pass, you start off with a round rod, which is fed into a rectangular channel. There's a roll to press that into the die, and then this moves through some arc and then exits. Now, the angle at its exit is whatever you want it to be, at least for the machines at Fort Wayne Metals. But in this case, we used 120 degrees. Okay. The billet that comes out is rectangular and, of course, can be fed in generally by your out BC again and again and again. Okay, so that's pretty classic and well established. Characterization, again, this is just showing some sample preparation. It also shows one of the billets here as it's being sectioned. We're looking, everything we look at, we'll be looking at longitudinal sections. So these things are cut out of longer bars, and then put in a vibromet and polished to a mirror finish for 14 hours so that we can take a look at the microstructures. We'll also take those same bars and make them into tensile samples. In this case, microtensile samples, about 2.5 millimeters in diameter here. We'll pull those at a conventional quasi-static strain rate and test them at 20 degrees C. And then also do Vickers microhardness, and there's one of our Vickers testing machine. I'll note that we used high temperature extensometry for this. So had we wanted to test temperature dependence, we could have done that, but chose to just get conventional properties. Okay, so let's look at some results. So when running at lower temperatures, 100 degrees C in this case, we see indeed the occurrence of the shear banding and actually shear cracking in some cases that show up. And this was done at a feed rate of 6.3 millimeters per second, at least the result I'm showing here. So that's an unacceptable temperature for working with 316. But if we run at 300 degrees or above, then we get stable flow at all rates. And so there was no evidence of macroscopic strain localization. There is some microscopic localization, and we're going to talk about that. But anyway, regardless of the speed, and I guess the comment I would make from this is you look at these billets. Now these are, we eventually stopped using 1 meter, just so we don't need to demonstrate with that length. So most of these are on the order of 120, 150 millimeters in length. But in any case, run back to back through the ECAP or continuous ECAP machine. And again, here we're able to get up to rates that are really limited by the machine itself. Had the machine had a little bit more power and more rigidity in the tooling, we would have been able to run it at faster speeds. So we weren't actually really able to test the limit from a material standpoint, but we were able to get to rates much higher than we would have expected. Okay, now for microscopy, we looked at really just 4 of the conditions, 4 passes, 6 passes, 2 passes, and 5 passes, and it rates from 12.7 millimeters per second to 36.1. And we chose these and these particular samples because they were ones that the rods had beautiful surface characteristics and were very amenable to conditions that we could actually use in production. All right, so EBSD shows us a couple things. And because I'm not doing this in presentation mode, there's some overlays that show you the presence of where we have stable shear bands, which I would have scrolled in here. But in any case, what you see here is EBSD, and these are again longitudinal views. The extrusion direction is horizontal in this image, and in the 2 images on the upper portion here are for one of the lower rates, 12.7 millimeter per second, and then as we go to 25, and then finally 36, a couple things that show up. So now there's a comment that I wanted to make about just conducting EBSD, but I think I'm going to leave that out here just in the interest of keeping to time here. But anyway, what you see, of course, is a fine structure, a fine grain structure that shows up. And actually not with a really strong texture. But what you also see is these, in inverse pole figure maps, and here you can see the color code here, are superimposed on the image quality maps, which give you an indication of where we have regions with higher dislocation densities. Now we're also able to plot, CAM, kernel average misorientation maps to also look at dislocation density, but the those are somewhat similar to what we end up with the IQ maps as well. So those are superimposed. So where you see greater darkness, you also tend to see where you've got higher dislocation densities and also some indication of the shear bands. So you can see the bands orienting at inclined angles, and in all of these, angle is always the same. But nevertheless, those bands do not develop to be unstable. Now, when we look at the tensile curves, you'll see there's a little bit of indication of some lack of heterogeneity. But for the most part, we get reasonably spaced and reasonably stable shear bands that resist undergoing catastrophic failure. You can see this a little bit also if you look at the grain boundary misorientation maps, where you see examples of these inclined features. The key here shows the misorientation angles. And again, the images, the EBSD generated images, are in the same locations as they were previously. So here we see the highest rates here. Now you see lots of low angle boundaries in here because there are plenty of subgrains that also show up in all of this, which we differentiate from the grains. Now, what are the grain sizes? Now I'm showing the grain size maps here in a way that—
I'm sorry, I interrupt you. You have 5 minutes.
Oh, thank you. I appreciate that. I'll be able to finish in 5 minutes very easily. Okay. So first of all, so let me just quickly summarize so we leave some time for questions as well. So we get a grain size on the order of 300 nanometers, 0.3 microns, except in this uppercase, which I'm not going to comment. But these are plots of grain area versus area fraction. And one of the nice things about doing that, if we look at these lower plots, is that you can see the development of a bimodal distribution of grain sizes. You see this tail that shows up here more readily if you use area-based plots. So I don't think I'll comment more on that, except the main point is that we're getting submicron grain sizes. And the second point here is the textures are somewhat moderate. These are inverse pole figures, again, looking at the transverse direction. And so you see the classic shear texture, though I'll comment that if you're on an uneven number of passes, 5 passes, you see something a little bit different there. But the key point is that the texture, the maximum times random here is between 2 and about 4. Okay, now if we compare this to work of others, we see that, and this is work by Gregor, you see the people in Ostrava, in the Czech Republic, at VSV. In any case, they also see some evidence of shear banding, and they get tensile properties that look like this. So they're doing ECAP with 105-degree dyes, and they're doing that at temperatures that are not specified, but they're in the range of room temperature to 290. And they find tensile strengths in the range from 900 up to just above 1100. Now, if we look at our tensile properties, they're somewhat comparable, a little bit lower. Our strains are a little bit smaller, but what you can see here, and these are the actual tensile curves for the series of samples that we looked at the microstructures at. And here we see that, again, tensile strengths are, UTS is reached at a small strain, but you have a lot of post-uniform ductility, generally exceeding 20%. Okay, and again, what we find is that we get the highest strengths for the highest rates, but quite frankly, what made the most difference, of course, is the absolute accumulated strain and the not so much the strain rate. We also looked at, and these are the actual figures. So the highest strength that we got here was about UTS was just over 1,000, 1 GPa. As people know, microhydrous doesn't generally correlate very well with tensile strength. And we found the same, but one of the reasons you look at it is, in production, you want to have fast ways to try to determine whether you've got a suitable set of properties. So for, of course, hardness has only a weak correlation with tensile strength. And so you can see 4-pass, 5-pass, 6-pass increase in strain, but interestingly for the 2-pass, we're way down here, and the correlation with hardness is not so good. So let me just conclude by pointing out that we were able to produce submicron grain sizes in a stable way in 316 LVM at 300 C. There are shear bands that form microbands, but they remain stable even at feed rates up to 42.5 millimeters per second. The strength gets up above 1 GPa with preserving 20% elongation to failure. So far beyond, almost an order of magnitude greater than what you get with conventional metal forming. The strength depends more upon the total strain than the feed rate. And then finally, the rates are fully adequate for doing industrial commercial production. And with that, I want to thank you. And if there are any questions, I'll look for those in the chat or answer them directly.
Thank you, Professor, for such monumental research. And thank you for your attention. I know it was difficult because you have early morning now.
Yeah. No, I'm used to that though. But yeah, it's a pleasure to be with you, and I will remain with you here this morning.
So, colleagues, do you have any questions?
Dmitry, may I have one question? Terry, thank you very much for exciting, because especially for technical auditory, this your lecture. My question regarding ductility. Of course, you showed the total elongation after ECAP conform quite large, about 20%. But I saw this is not uniform elongation. Uniform elongation is really low. In this case, we can expect fatigue properties will be not so good, fracture toughness. Have you tried to improve uniform elongations?
So Ruslan, thank you for the question. At this point, the answer to that is no. And that's in part because most of our focus is on titanium and titanium alloys. So this was exploratory. But the other point is that we would not measure the properties in just this state. Is that as you, of course, well know, and your colleagues who are incidentally want to acknowledge as being literally the pioneers for making this kind of technology possible. In any case, there's always some post ECAP-C process that's applied as well. And whether that's swaging, rolling, or drawing. So it's only after that point. So we haven't gotten to that stage yet. So that's the next step, is to let's say, swage these and then definitely look at
okay, and then you will be try also to investigate the service properties, yes?
Yes, and including fracture response, fatigue, really everything.
For any application, it's important. Thank you very much. Yes,
you're welcome.
Yes, very interesting.
And also we have one question in chat from Roman Kulagin. What is the difference between C ECAP and the conventional conform?
There are a few minor differences, but probably the most significant difference is that the word conform is actually a registered trademark that belongs to BWE. And so it's a deliberate choice not to use that trademark because so Fort Wayne Metals, so it's one thing for a university or a researcher to do this, but Fort Wayne Metals is not a university. They are a metals producer. So it's not really legal for them to use someone else's trademark in describing the process.
So colleagues, do you have any questions? No, thank you.
All right, thank you very much.
Thank you. So we should go to the next reporter, Targom Akapian from National University of Science and Technology, Mrs. We have a pre-recorded presentation.
No, Dmitry, Dmitry, thank you. I am ready to make online.
You're welcome.
Thank you. I'm ready to share with the screen. Okay, colleagues, can you see my presentation?
Yes, everything is okay. You're welcome.
Thank you. So my name is Akapian Targom, and today I would like to talk about the aluminum alloys, especially aluminum copper-based alloys, with the minor trace addition. So the content of the presentation on the slide, and it should be noted that aluminum copper alloys are one of the most used among the aluminum alloys in the industry, because they're a very good combination of the strength at both room and elevated temperatures. And of course, it is necessary to additionally improve the mechanical properties. Actually, there are several ways to do that, and one of the most widespread is additional alloying with low alloy or trace additions. And in this case, I can note that the type 2519 types American aluminum alloys, which contain magnesium and silver trace additions, which facilitates the formation of the omega phase instead of the conventional theta prime phase, and more uniform distributed precipitates, more finer precipitates, leads to increase in the strength, as we can see from this graph. However, it is obvious that the wide usage of the silver in the industry, it is very limited, and it is necessary to find alternatives, and one of them can be the cadmium addition in the aluminum copper alloys. Indeed, as we can see from this graph, a minor addition of the cadmium leads to the significant increase in the strength of the aluminum copper alloys due to the significant refinement of the precipitated structure. However, due to the extremely toxicity of the cadmium, its wide usage of the industry also very restricted. In this case, using the tin or indium trace addition can be very fine alternatives of the cadmium. Indeed, as we can see from this graph, 0.05% weight percent of the tin in the aluminum copper-based alloys leads to significant increase in the strength and in the precipitation hardening response rate due to the significant refinement of the precipitated structure, theta prime structure phase. And to date, there are several theories trying to explain this phenomena. However, this phenomena still remains very controversial. I mean, the based mechanism. However, despite of this, it is obvious that this phenomena has a very great practical importance. And surprisingly, in the literature, very few works exploring the influence of the different conventional processing, such as formation or rolling, on this phenomena. So in this work, we try to make some observation about the influence of the tin trace addition on the microstructure and mechanical properties of aluminum copper-based alloys after the casting, heat treatment, and metal forming. For this purpose, we chose two alloys: the base one binary alloy and ternary alloy with 0.1 addition of the tin. So the advanced technique was used for the analytical analysis, such as electron microscopy, atom probe tomography, as well as hardness measurement, specific electrical conductivity measurement, and analysis of phase compositions using the thermodynamic calculations in the thermocalc program. So, as you can see from this vertical isoplev, calculated at the varying content of the tin, the maximum solubility, according to the calculation of tin in the aluminum, can reach about 0.5 weight percent, which seems is very overstated. Nevertheless, as we can see, for the alloys up to this content of the tin, we can expect also the reappearance of the liquid due to the significant decrease in the tin solubility with the decreasing of the temperature, and the true solidus of the alloys corresponds to this red line horizontal, horizontal line, which temperature is quite close, is equal to the melting point of the pure tin. So it seems no reasons to over-alloying the aluminum copper alloys with the tin more than 0.1% due to some problems which can cause the excess content of the tin. And as we will see below, it is really it can be confirmed. So let's see the microstructure of the alloys in different states. For instance, at the top of the slide, we can observe the microstructure of the base alloy in SK state and after high temperature homogenization. We can observe in SK state a relatively coarse structure, SK structure containing the stable theta phase from the non-equilibrium eutectic, which actually after the high temperature processing almost completely dissolve in the aluminum solid solution. For the ternary alloy with the tin addition, we can find out some differences in the structure, especially in the SK structure. As we can see, a significantly finer structure we can observe, and this structure is caused due to the appearance of the very fine, tiny tin inclusions associated with the theta phase, leading to such kind of refinement. So after the high temperature homogenization and quenching, we still can observe the existence of some small tin inclusions, which suggest that significantly far lower solubility of the tin in the aluminum than that predicted by the calculation, and even than the 0.1, and seems no reason for alloying these with this element more than 0.1%. Actually, it should be even lower. So the microstructure of the alloy was analyzed using the micro-PROF analysis in SK state and after quenching, and most interesting, which we can see from this table, is that the tin solubility is too low and low the tool sensitivity threshold to arguing about its solubility in aluminum. However, after the high temperature annealing and quenching, we can observe the significant increase in the tin solubility for speculating about its noticeable solubility in the aluminum. So after the quenching, the alloys were subjected to the aging, and micro hardness and electrical conductivity was measured during the process. And as we can see from this graph, the hardness of the ternary alloy rapidly increases within first 2 hours of aging, and reaches the peak value and then remains almost unchanged. In contrary, we can observe very moderate increase in the strength of the binary alloys during the first 8 hours, and then we can observe additional increase. However, the peak value of the alloy is significantly lower than the peak value for the ternary alloy. Electrical conductivity also of the ternary alloy is significantly higher than for the binary alloy, which means the more deeper and complete decomposition of the aluminum solid solution during the process for the ternary alloy than for the binary alloy. Analysis of the spine structure of the alloys after them in the peak age state reveals that indeed trace addition leads to significant refinement of the theta prime precipitated structure. For the base alloy, we can observe about 2 times decrease in the size of the precipitates for the ternary alloy, while the number density is increased about two times compared to the binary alloy. So atom probe tomography reconstruction of the structure of ternary alloy at the peak edge state reveals the 3D disc plate-like shape of the theta prime precipitates, and some of them are incorporated with the very fine particles enriched with tin. And these results allow speculating about the possibility of prior formation of these fine tin particles, which then act as the sites for as the effective sites for the nucleation of the theta prime phase. However, as I said above, the actual mechanism tried to additional studying. So after that, we confirmed that this phenomena is working for these alloys. We started to deformation processing. Two routes were used, and they characterized with hot deformation process and or cold deformation process. After deformation, the alloys were subjected to the solid solution treatment and again aging at the same temperature as for the ingots. As can we see from this graph, after the processing route 1, means after the hot deformation and solid solution treatment, we can also observe this accelerated increase in the strength of in the hardness of the ternary alloy compared to the binary alloy. The peak value is about the same as for the ingot, and for the binary alloy, in contrary, we can observe even moderate decrease in the strength during the first 2 hours of aging, and then also the moderate increase. The electrical conductivity of the ternary alloy also higher than that for the binary alloy by the same reasons as for the ingots. After the cold rolling, we can observe the same. The hardness of the ternary alloy increases much faster, and the peak value is significantly higher than for the binary alloy, and the same for the electrical conductivity. If we compare the influence of the actual type of the deformation, cold or cold deformation, we can see that for these model alloys, there is no really high difference between the update hardness after the processes. The difference is quite low, and no really reasons for the cold deformation instead of the hot deformation. So as a summary, I would like to emphasize that the alloys with the majority of alloys with the trace addition of tin should solidify at temperatures below the 230 degrees, which is close to the melting point of the pure tin. And actually, according to the microstructure analysis, the actual solubility of the tin in the aluminum solid solution is much lower than that predicted by the calculation, and should be lower than the 0.1%. And to find out the actual solubility of the tin in aluminum, it is necessary to continuing the more precise investigations. And then it's necessary to note that whether, despite the actual state of the alloy, whether ingots or deformed semi-finished products, we can observe the significant influence of the tin addition on the hardness and electrical conductivity of the aluminum copper alloys. For instance, we can observe the significant increase and in the precipitation hardening response in the peak value, and in the significant reduction in time of reach this peak value. So we believe that this approach is very promising for the further studying and to constructing the alloys for the real industrial applications. Thank you very much. I'm ready to your questions.
Thank you for your report. Colleagues, questions?
This is Terry Lowe. Just a quick question. Very nice work. Thank you. So the aluminum conductors, or aluminum for, yeah, you noted, of course, that you improve the electrical conductivity. Aluminum conductors are most commonly continuously cast. I'm curious how the addition of tin affects the ability to continuously cast this alloy.
Yeah.
Do you know?
No, no, we didn't study in case of the continuing casting, and this alloy is not for the conductive conductive applications. It's just a construction materials, and electrical conductivity study is necessary to analyze them more deeply the processes which accompany during different phase transformations. So,
I understand. You're just using it as a tool for investigation.
Yes.
Yeah.
Yes.
Very good. All right. Thank you.
Thank you for your report. Next report is is going from Padova University. I hope.
Yes. Can you hear me?
Yes, Alessio. Hello.
Very good.
Buongiorno.
Buongiorno. Good afternoon to everyone. I share the screen. Sorry. Can you see? Very good. For me, it's a pleasure, and I describe a preliminary result of a work entitled Effect of Substrate Briefing on Duplex Laser Welding. It is a collaboration with University of Sao Paulo in Brazil, and concerning the welding of the duplex stainless steel. Firstly, a brief introduction. Duplex, when subjected to welding processes, as an unbalanced microstructure, and then we obtain a predominantly ferritic microstructure, which compromises mechanical properties of the steel and also local pitting corrosion. For a welding process, it was choose a neodymium YAG pulsed laser because this process has various advantages compared to conventional processes. Indeed, it is possible to obtain a complex shape welding and high accuracy. Also, we have a short cycle time and a low if input and a narrow if affected zone. However, the low if input employed and the high cooling rates, typical of these processes, promote the formation of ferrite, resulting in an unbalanced microstructure with a low austenite content in the weld joint. Then there were a lot of solutions to obtain a balanced microstructure. It is possible to perform a treatment after welding, but it creates some problem concerning cost because you have to perform a longer time treatment. It is possible also to add austenite forming element in the weld joint. For example, it is possible to use nickel or nitrogen. And the third, it is possible to brief the sample before welding. For this work, it was chosen the briefing of a sample before welding. The composition of the steel employed is given in the table below, and for performing the welding test, it was selected a sheet of 1.5 millimeters of thickness. The welds were performed employing a system formed by a neodymium YAG solid state laser impulsed condition. Two conditions were selected with the same welding parameters described in the table below. The peak power of the laser was 2.0 kilowatt. The pulse duration was 5 microseconds. The frequency selected was 9 Hz, and the welding speed was 1 millimeters per second. The two conditions evaluated were welding at ambient temperature and welding after heating the sample in a range between 200 and 400 degrees Celsius. The welding was performed with a single pass, and the shielding gas used was pure argon with 20 liters per second of flow rate. Oh, sorry. The characterization, firstly, it was performed some CAM analysis on base material and welded zone. For some analysis was selected the Birha reagent in order to reveal microstructure. The occurrence of secondary phase was tested with a SEM micrograph without chemical etching. The presence of austenite and ferrite was verified both in fusion zone and the INF-affected zone. On future, we perform some XRD analysis and some image analysis in order to evaluate a value of a fraction of ferrite and austenite. Then it was performed a microhardness profile, a Vickers microhardness profile on cross section. And in the end, it was performed some corrosion test, some CPT, critical pitting temperature test. These tests were performed according to standard ASTM G105. The solution employed was 1 molarity of sodium chloride. We can this way evaluate the corrosion resistance. The slide describes the semi-microstructure of fusion zone. In this type of steel, in welded zone, it is possible to see 3 different austenite mode, allotropomorphs grain bounds austenite with mastaten austenite, and also it is present in granular austenite. In particular, if we consider the ambient welded sample in this SEM micrographs, it is possible to see the presence of a high quantity of ferrite and a low quantity of austenite only in grain boundaries. Instead, in pre-filled samples, it is possible to verify the presence of a high quantity of austenite, not only in grain boundaries, but also we have intergranular austenite. And for this way, it is the pre-filling promote the formation of austenite in fusion zone. Also, we studied the microstructure of transition zone between base material and fusion zone. If affected zone, it is possible to observe a higher quantity of austenite, in particular intergranular, in the pre-filled sample compared to ambient welded sample. So in this way, the pre-filling treatment can lead to a quite phase balance in the weld joint. Then it was performed the Vickers microhardness profile, as shown in the picture, and also we calculate the value. And it is possible to see that the sample welded at ambient temperature show the highest microhardness value. This is due to the predominance of a ferritic microstructure. The increase of austenite content in the joint decreases the hardness value in the fusion zone, as it is possible to see in the pre-filled sample. Moreover, we can verify that there's a different values of the microhardness of base metal in the two conditions, in the ambient welded sample and in the base material. This is due because the briefing leads to a slightly increase in a grid dimension in the base metal of the briefed sample. In the end, it was performed pitting test, CPT test. It was verified that at ambient welded sample show the lowest critical pitting temperature due to the high ferritic volume fraction in the joint. The pre-feed sample instead has a good behavior because of austenite formation in weld joint. Indeed, its CPT is higher of 14 degrees Celsius compared to ambient welded samples. However, because in if affected zone, the microstructure is quite unbalanced with ferrite formation, the CPT is lower compared to base metal. Indeed, the base metal has the best corrosion performance, showing the highest CPT temperature. In conclusion, the briefing treatment of a sample influences the formation of austenite, both in quantitatively and in qualitatively way, modifying the volumetric fraction of austenite. The ambient welded sample instead is characterized by an high amount of ferrite in weld joint. Then microhardness of a weld joint decreases with increases of volume fraction of austenite in the welded joint. In particular, it is possible to observe that pre-feed sample has a low microhardness compared to the ambient welded sample. In the end, the pre-feed sample has a higher corrosion resistance compared to the welded sample, and this is highlighted by the increase of critical pitting temperature. Then thank you for your kind attention, and sorry for my not the best presentation.
Thank you for your presentation. Colleagues, do you have any question?
Sorry, can you repeat?
No, this is I ask colleagues for questions for you. Okay, I have one question about size limitation for such welding. Maybe just your prediction. What the biggest size of billet you can treat by this this type of process?
Sorry, I don't heard. Sorry, can you repeat?
What the biggest size, what the size limitation for such treatment?
The size limitation. I do not perform the test. I received the sample prepared by Brazilians, and yes, I don't know these parameters.
Because I think for process with I don't know 10 millimeters. It could be
yes, I think 10 millimeters is the maximum.
Yes, because high cross section it will be a little bit difficult.
2-3 millimeters.
Yes.
Okay.
2 or 3 millimeters is the maximum size that can be welded with this system.
Okay. I understood.
Okay.
So, colleagues, do you have any questions? No. Thank you. Thank you for your report. And next report goes from National University of Science and Technology. Mrs. again, Pavel Shurkin. Is it correct?
Yes, it is.
Yes.
I would be grateful if you could start my pre-recorded presentation.
Так, а вы мне ее присылали?
Yes. Or I could start it myself.
Если не сложно. То есть у меня, к сожалению, ее нет.
Minute, please.
No problem.
Oh, I do apologize. I hope my very good presentation will be clear for you. I'm going to demonstrate my screen. Can you see it?
Not yet.
Now?
Yes, yes.
Okay. Excellent.
We don't hear you. В общем, когда нажмите новую демонстрацию экрана, и в углу поставьте галочку в левом нижнем «Совместный доступ к звуку». И тогда мы вас будем слышать.
Dear ladies and gentlemen, my name is Pavel Shurkin. I'm from National University of Science and Technology MISIS, Department of Metal Technology. Happy to present my research at Magnitogorsk Materials Week. It is going to be about influence of calcium, iron and silicon on the aluminum zinc magnesium alloys upon casting. My short presentation includes introduction, description of idea, methods and results we achieved on characterization of the cast ingots and rod products. So aluminum alloys are very popular, and the strongest ones are 7000 alloys. Their application is very wide, and for example some enclosures for mobile phones are made from this material. However, having that there are a lot of research nowadays dedicated on this material, there has been no sustainable advance yet. 7000 alloys containing zinc and magnesium are prone to hot cracking and welding is quite impossible. They are intolerant to impurities and complicated in processing road. If the chemistry or technology are minorly deviated, it will show its worst qualities like intense intergranular corrosion and brittleness under stress. Moreover, it should be noted that in our university we collaborate with pivotal aluminum companies like Rusal and so on, whose efforts were given for developing of the new Russian standard on the wrought aluminum alloy. In addition to some traditional types of 7000 alloys, the novel AZ6NF has been introduced as an iron-tolerant material which moreover can show good performance in welding, both due to formation of the tectic reaction and specific solidification behavior. However, as it contains nickel, it appears to be costly for industrial widespread. On this basis, our team is working on calcium-containing alloys. Calcium may act as an alternative to its active form in silicon and nickel. Our preliminary results showed that it may increase casting properties and also bind iron and silicon into ternary phases. However, up to date, there has no previous research conducted on aluminum, zinc, magnesium, calcium alloys containing both iron and silicon. In this respect, we took the same ideas applied to nickelines. AZ6NF, it is desirable to achieve the multi-phase adaptic microstructure with no iron and silicon bearing binary phases. According to the principal designs designed in the book presented here, the important formation of the multi-phase adaptic is stipulated by substantial differentiation of the microstructure due to increase in the net volume fraction of the atactic phases, providing a similar effect as it is due to increase in the cooling rate. So under this condition we will have far more curved and differentiated intermetallic phases in the microstructure, and probably very small dendritic cells. Indeed, also the cooling rate must be controlled as a part for tuning solidification, and finally the microstructure must be appropriate for the treatment. Homogenization. It is used for stress relief, dissolving of non-equilibrium phases, and shaping of the insoluble phases up to their spheroidization. The latter, for example, is widely used in 6000 alloys for the transformation from beta ion to alpha ion phases. Also on the right, you can find some preliminary results, and we can see that high amount of tectic phases in the microstructure may allow us to avoid grain boundary weakening in comparison to the base alloy, and moreover, for the sake of comparison, we obtained several alloys. The two ones are the base alloys without any tectic forming insoluble elements. The second one contains iron and silicon without calcium, and two alloys with 1% and 2% of calcium, both alloyed with iron and silicon. The solidification was studied by thermodynamic method employed with thermocalc software. Also, we used traditional casting methods for obtaining the experimental samples, and they were further subjected to heat treatment, hot and cold rolling, and we studied the samples by SEM and OM microscopy, measured hardness, and determined the tensile properties. We start with the characterization of the ingots of the solidification. Here you can find the results of our thermodynamic calculations. It is a polythermal section, depending on the ion content and fraction of phases on the temperature. It looks a bit complicated. It should be noted that the current available databases are quite limited in case of calcium-containing alloys. It shows the appearance of aluminum-calcium-silicon phase, but doesn't count the solubility of zinc in aluminum-calcium phase and formation of aluminum-10 calcium iron 2 phase. However, it can be exactly concluded that the alloys have enough high equilibrium solidus. The fraction of the tectic may achieve 10 mass%, so that in this respect we may conclude that the alloys may be subjected to two-step heat treatment, one of which is for dissolving of non-equilibrium of tectic, and the second one is for tuning the shape of the intermetallic phases. Presented in the microstructure. When considering as cast structures, the base alloy is not presented here. It contains an aluminum matrix which is decorated with zinc and magnesium rich tectic, and with the addition of iron and silicon, the structure becomes more complicated, but quite clear in the presence of the dark magnesium 2 silicon phase and iron containing phase as a Chinese script. Both these phases are quite undesirable for 7,000 alloys, and with addition of calcium, the structure becomes far more complicated, and it is very difficult to reveal any phases in the microstructure. In particular, the alloy with 1% calcium looks a bit favorable, than the alloy that contains 2% of calcium. The latter contains high amount of needle-like phases, that is probably to be aluminium calcium silicon phase, and was substantiated in our previous research on the alloy which do not contain iron but only silicon. So when going into the details of the microstructure of 1% calcium containing alloy, we have studied it with electron microprobe analysis and revealed the presence of high amount of different phases like aluminium calcium silicon, the solubility of zinc in aluminium calcium phase. Also, it contains non-equilibrium tactic and low amount of aluminum 3 ion that is a bit coarse but very fine in the thickness, and so we may conclude that after heat treatment it have a potential to be tuned up to spheroidization, and this claim was substantiated by the results on the microstructure after ionization heat treatment. While the alloy containing iron and silicon shows no change in iron containing phase, the alloy containing 1% of calcium shows almost completed spheroidization of intermetallics. It is very fine and favorable for the hot rolling. Here you can see the pictures of the hot rolled sheets, which are mostly successful except from the alloy containing 2% of calcium. The latter was crushed probably due to presence of the coarse intermetallics in the initial microstructure. When considering the microstructure of the hot rolled sheets, we put attention on the following condition after hot rolling and intermediate annealing at 250 degrees centigrade, and after intermediate annealing followed by furnace cooling to reveal grain boundary precipitates. The latter is very important for high strength aluminum alloys of 7000 family, because it causes the low fracture toughness and corrosion under stress. So we can see that in the initial condition the base alloy contains high amount of secondary precipitates containing zinc and magnesium. After intermediate annealing followed by air cooling, low amount of grain boundary precipitates are quite clear, and their growth is also clear after furnace cooling, and we can see that grain boundaries are very weak, and these precipitates are very coarse and are clearly seen even by our microscopy. Actually, the other alloys do not contain these such coarse secondary precipitates, but the alloy containing iron and silicon shows a high amount of strings and conglomerates of intermetallics in the microstructure, and there is also almost no difference between the microstructure in different conditions. The same picture may be seen in the microstructure on 1% calcium containing alloy, but it shows far more uniformly distributed intermetallics in the microstructure, and it looks far more favorable for better mechanical properties. When considering the grain structure, the high amount of uniformly distributed intermetallics may act as a for providing pinning effect, and we can see that after intermediate annealing, the microstructure of calcium-containing alloy is far more elongated, and the recrystallization were not completed in comparison to the situation in the base alloy and in the alloy containing iron and silicon. All the alloys which showed good performance at hot rolling also showed very good processability at cold rolling down to 0.5 millimeter. That is corresponded to 95% reduction in comparison to initial cast ingot. They were cut and subjected to tensile test, having the results for the grain bond weakening and intermetallics behavior. We conducted tensile test for two conditions, one of which is related to T6 condition for maximal strength achieving and overage condition. As we can see, the calcium containing alloy is very competitive, and the values for mechanical properties are far better for both conditions. Actually, it far more clearly seen that the elongation is very high for the condition T7 that is overaged, and we can see that the base alloys showed intergranular fracture, and the calcium containing alloys show a high amount of dimples. And on this slide you can see how the experimental alloys behave under the strengthening heat treatment. In addition to the alloys presented in the previous slides, you may see the alloys which contain only calcium without addition of iron and silicon, and their behavior looks far more different because of the dissolution of the zinc and aluminum calcium alloy, and this effect shows lower hardening response upon aging because of lowering of the effective zinc solubility in the aluminum solid solution after quenching. In comparison, the alloy containing 1% of calcium, iron and silicon shows very good hardening response that is very similar to the response of the base alloy, and they show very similar results on the T6 heat treatment for maximal strength, and the numbers are about 200 points on Vickers hardness. In the end, having the results presented and some trial and error experiments, we proposed the novel alloy containing less zinc and magnesium and reduced in C content for elimination of the aluminum calcium silicon phase growth. It shows a very favorable uniform microstructure in each step of processing and exhibit the mechanical properties comparable to commercial 7000 alloys, but also competitive in less tendency to grain boundaries weakening and the uniform distribution of precipitates as it's shown in our TM microstructure. We suppose that each new interfacial surface appeared due to presence of eclectic phase act as a nucleiform precipitation, and the sites the seen for vacancies. Therefore, this distribution is very uniform, and precipitates free zones along the grain boundaries are not very wide as it is in the base alloy considered, and also most 7000 commercial alloy. Thank you very much for attention. In the end of last year, I won the Metals Travel Award and would like to thank the Journal Metals for the financial support they provided. Here you can see my contacts. You're welcome. Please feel free to ask any questions.
Thank you for your report, Professor Pesin.
Yes. May I ask one question? You, in your research, you study influence of several elements for strength and ductility and structure. And what is your opinion? Maybe the regions of the rolling could influence for structure, maybe for ductility and strength. For example, you can you can have reduction 80%, and you have maybe 8 passes for 10%. And what is your opinion? The result will be the same or maybe different?
Павел, мы вас не слышим.
Sorry. In my opinion, they will be different, and this investigation have sense only prior to industrial assessment, I think, prior to really large scale road products, and when we study our samples in the laboratory scale condition, they are almost uniform. And as you may have seen in the last slide, the hot rolled products and cold rolled products with quite different structures were had quite same mechanical properties, but I can claim that they will be the same under the industrial conditions on the large scale products with different reduction rates.
Thank you.
I hope you understand.
Anyway, you can collaborate and test this idea on your new rolling mill, Professor Pesin.
Yes, it will be a pleasure. Thank
we
you.
We are collaborating with Mrs. now. Yes, we are.
Okay.
We are contact. Yes.
So, any question?
Yes, one more, please, Dmitry. Can I ask?
Of course.
Yes, I don't know, Pavel, could you open the slide where the micro hardness during the aging are shown? Nevertheless, on this slide, we can see that when you add the iron together, the calcium, the increase of the alloy is
the
hardness of the alloy is increased.
Yes.
And how can you explain this influence?
Hardness of what alloy increased? Indeed, the hardness of all the alloys present.
I mean the alloy with
aging.
Yeah, I mean the alloy with iron.
Yep. When considered aluminum, zinc, magnesium alloys, their hardening is explained by precipitation of zinc and magnesium rich precipitates, which are very fine. On the other hand, iron does not influence on this precipitation, while silicon may have this influence. And here you can see that iron and silicon containing alloy have a lower hardness than the base alloy. So the behavior of precipitation is the same as in the base alloy, but it strongly depends on the composition of the aluminum matrix.
Thank you, I see, but I meant that if I right understood, the zinc can dissolve in the aluminum for calcium phase.
Yep.
However, when you add together with the iron or with the silicon, the phase equilibrium can change. And so the amount of the aluminum for calcium can be reduced. And so the zinc can be
you're absolutely right. So the amount of aluminum zinc calcium phase is reduced due to formation of ternary phases with calcium, iron, and silicon. So that we have such an effect presented on this slide.
Yes, thank you very much.
So, colleagues, we should go to the. Thank you for your report.
Thank you very much.
We should go to the last report today. We don't have a report from Marina Samadurova, but we have one report from yesterday from Valery Danilenko, Institute of Metals Plasticity Problems, Russia. So you're welcome. Thank you for your attention.
So, good day, dear colleague. Can you see my presentation?
Yes, everything is okay.
Good. The first, thank you for the possibility to speak at conference in memory of Alexander Petrovich ZHILYAEV. The report is good. Kappa aluminum metal matrix composite fabricated by accumulative high pressure torsion. My name is Valery. My colleagues Leila Kiyikuzhina and Dmitry Gunderov. It is content my presentation, high pressure torsion and its evolution, accumulative high pressure torsion. 3-layer stack, kappa, alumina kappa, metal matrix composite obtained accumulative high pressure torsion and other investigation method. Bulk nanostructure materials are obtained using several plastic deformation method. High pressure torsion is one of the unique several plastic deformation method. A significant contribution to the development of this method was made by Alexander Petrovich ZHILYAEV. Just look at the list of his publication dedicated to high pressure torsion presented in this slide. This is the first review on the high pressure torsion method, 2 monography or 2 books on this topic, including the one that come out this year. In this book, the 3rd chapter is about high pressure torsion. Evolution high pressure torsion may be called accumulative high pressure torsion. Dmitry Gunderov and your colleagues proposed to develop the high pressure torsion method as accumulative high pressure torsion. The essence of this method is that the deformed sample by the high pressure torsion proceeding and cut into 4 parts. This part stuck in on anvil and deformed under the same condition. Cut and deformation, such cycle can be carried out several times. My goal of this report is a comparison of structure kappa aluminum metal matrix composites fabricated by traditional high pressure torsion and accumulative high pressure torsion. In this slide, you see traditional obtain kappa aluminum metal matrix composites proceeds by high pressure, traditional high pressure torsion. In this slide, cuprum alumina metal matrix composites processed by a cumulative high pressure torsion. 3 layer kappa, alumina kappa, stuck on anvil and deformation, cut into 4 parts, stuck and stuck it on anvil and deformation under the same condition, and obtain this subject, this object, this disc, this metal matrix composite. It is samples for investigation made traditional HPT 3 layer kappa aluminum kappa, pressure 6 GPa, room temperature, rotation speed of 1 rotation per minute, and 10 turns processing. Accumulative high pressure torsion, it is similar, but step 1, 3 layer disc kappa, alumina kappa, deformation in this condition, and 2 turn. Step 2, cutting on 4 parts. The parts were stacked on top of the high pressure torsion anvils on top of each other, and revolution 2 turns. Repeat cutting 3 times. The step 3, after third cutting, the stack was deformed by 4 turns. Scanning electron the cross-section structure was investigation in detail of the zone of the center and the edge obtained sample. This is sample after traditional high pressure torsion. It is same picture. The bright region denote kappa rich phase, this and this, and the dark region denote the aluminum rich phase, and left, and it is composition map for kappa element, and this green and red, it is element of alumina. You see very small mixed this disc after accumulative high pressure torsion, the accumulative high pressure torsion gives strong mixed in the center. Composition maps confirm this. It is scanning electron microscope. It is composition map or element map. Kappa alumina. The edge after high pressure torsion. You see a weakly mixed structure, and the edge on sample obtained traditional high pressure torsion. This edge after accumulative high pressure torsion, you see mixed at the edge on the sample, which is slightly weak than the center of this sample, but much more than the sample after the traditional high pressure torsion. X-ray diffraction analysis showed that the sample after traditional high pressure torsion contain only the red line contain only diffraction peak of copper and alumina. The patterns of sample fabricated by accumulative high pressure torsion, the blue line, confirm the present at aluminum, copper, and intermetallic compound, copper alumina 2 and copper 9 alumina 4. In this slide, you see fragment X-ray diffraction pattern from obtaining copper aluminum composite. You see intermetallic compound after accumulative high pressure torsion. This is my summary. Analysis by high ray diffraction, scanning electron microscope, and element NTDX method showed the formation of intermetallic phases in the lower structure during accumulative high pressure torsion. Thank you for attention.
Thank you for your report. Colleagues, do you have any questions? Okay, I have one question just for discussion. What do you think about industrial application of such method, high pressure torsion? Is it possible in perspective?
I think in present time we have only fundamental physical application, but solid state reaction and solid state reaction in metal. Как-то так.
Хорошо. So, colleagues, do you have any questions? Okay. Thank you for your report.
Thank you for you.
The second day is over. Tomorrow we have the last day of our conference. Please check the actual program on our website for some potential trouble. we have already sent link for program to all speakers of next day, and tomorrow we start at 8 a.m. In Moscow time, from report of Ayrat Nazarov. So please pay attention. The first report will be from Ayrat Nazarov. So thank you for your attention. The second day is over. Thank you for all listeners, speakers, for all participants from all around the world. Thank you. Bye-bye.
Thank you.